Welcome back to Cosmic Sedation, a place where dreams unfurl like soft whispers under the stars. Tonight's topic: what if we were sent to Earth on purpose? A thought-provoking journey through the ages. Don't forget to subscribe and give us a thumbs up if you're enjoying this as much as I am. Drop a comment with where you are tonight and what time you usually drift off into dreamland. And now, let's ease into the night together. In the year 4004 BC, according to one biblical timeline, humans discovered they were not alone in a universe governed by celestial matchmaking. The moment can be traced back to the first stirrings of philosophical thought around this time, when early civilizations began to ponder their origins. This was not just idle musing. It marked the beginning of an intellectual journey that would reshape human understanding over millennia. The surface temperature of Earth at this precise epoch hovered around degrees Celsius, a narrow band in which liquid water could exist, vital for life as we know it. Yet, long before humans appeared, our planet had been orbiting the Sun for nearly 4 billion years, an incomprehensible span that dwarfs even the longest human lifetimes. The earliest philosophers lived on a world where the average surface temperature was perfect for sustaining liquid water, but they could not have known about Earth's 4.54 billion year age based on modern radiometric dating techniques. These early thinkers were crafting narratives to explain their place in a seemingly infinite cosmos, unaware of the vastness beyond their immediate world. They lived within the habitable zone, an area around our star where temperatures allow for liquid water, a phenomenon that is both common and rare at once. Across the galaxy, trillions of stars exist, each with its own set of planets, yet only a fraction may host conditions similar to Earth's. For humans in 4004 BC, this realization would have been impossible. They could not fathom the vastness beyond their immediate world. Meanwhile, plate tectonics was quietly shaping their land masses, driven by heat from Earth's core at a rate of about 46 terawatts. Each time they gazed upon the horizon or stood on the edge of an ocean, they were witnessing the result of geological forces older than any known culture. The process of plate tectonics had been ongoing for billions of years, long before human civilizations emerged, subtly altering coastlines and creating mountain ranges through volcanic activity. This constant churning beneath their feet had sculpted continents and oceans over millions of years, long before human civilizations emerged. Earth's magnetic field, a mere 25 to 65 microteslas at the surface, shielded them from cosmic radiation and solar winds, allowing life to flourish uninterrupted by deadly space phenomena. This invisible shield was crucial for their survival, protecting them from harmful particles that could otherwise strip away Earth's atmosphere and make it uninhabitable. Meanwhile, they lived just 93 million miles away from the Sun, an orbit that allowed them to experience seasons and observe celestial cycles that would inform their calendars and religious practices. As these early philosophers looked up at night, they would have seen a sky unmarred by artificial light pollution, stars twinkling in all their glory. The atmosphere surrounding them was rich with 78% nitrogen and 21% oxygen, providing an environment conducive not just for breathing, but also for sustaining complex life forms. While these gases have remained relatively constant over the millennia, the concentration of carbon dioxide has fluctuated, playing a critical role in Earth's climate regulation. In this atmosphere, early humans could hear the rustling of leaves or the call of birds, unaware that their very existence was tied to the delicate balance of atmospheric composition and solar radiation. This realization would come much later, as science slowly unraveled the mysteries of our world's life support systems. The Earth's magnetic field is not static. It shifts and weakens over time, sometimes reversing polarity entirely. This phenomenon has occurred approximately 8 times in the last 3 million years alone. Yet, this dynamic field, with its current strength of around 25 to 65 microteslas at the surface, acts as an invisible shield, deflecting cosmic radiation that would otherwise bombard our planet's atmosphere. Without it, life as we know it might not exist. Imagine standing on Earth's surface during a solar storm, unprotected by this magnetic barrier. The charged particles from the sun would strip away the uppermost layers of your skin in minutes, turning you into little more than ionized gases. However, while the effects of cosmic radiation can be lethal to exposed organisms, they also trigger beautiful auroras near the poles. These displays are a visible testament to the magnetic field's protective role. The sunward side of Earth is always bombarded by high-energy particles, yet our planet remains shielded from the worst of their impact. This protection has been crucial for life forms that have evolved on Earth over millions of years. The strength and orientation of this magnetic field have guided migratory patterns for centuries. Creatures like birds, whales, and even bacteria navigate using tiny iron crystals that align with the geomagnetic lines. This natural compass has been crucial in survival strategies across species. For instance, monarch butterflies journey thousands of kilometers each year from North America to Mexico, following these invisible pathways. The magnetic field's subtle changes over millennia have influenced migration routes, adapting to shifts in Earth's geography and climate. In human terms, this could be likened to a global GPS system that predates any technological invention by billions of years. Remarkably, the coldest place in the known universe is not found in deep space, but within a laboratory on Earth. At temperatures approaching -273 degrees Celsius, colder than even the vast emptiness between stars, scientists have managed to create conditions where atoms nearly cease their motion entirely. This is a stark contrast to the average surface temperature of our planet at 15 degrees Celsius. The magnetic field, while crucial for life on Earth, does not directly influence such extremes in temperature. Rather, it protects us from cosmic influences that could otherwise cool or heat our climate unpredictably. Plate tectonics, driven by the convective motion of Earth's molten core at a rate of 46 terawatts, continuously reshape the planet's surface. As continents drift and collide over millions of years, the magnetic field lines are periodically distorted. These distortions can be observed in ancient rocks through their paleomagnetic properties, the alignment of iron minerals that record the orientation of the field at the time they cooled. This process has been ongoing for billions of years, with each shift potentially affecting the global climate and life distribution. For example, when the North Pole was located near what is now Greenland, it influenced ocean currents and weather patterns in ways we can only hypothesize today. The magnetic field's reversals are not just random events. They occur at intervals ranging from thousands to millions of years. During these periods, Earth's protective shield temporarily weakens, allowing more cosmic radiation to reach the surface. Such a scenario could have significant impacts on life forms that rely on this barrier for survival. Fossil records suggest mass extinctions may correlate with these times of magnetic weakness. Yet, despite these periodic vulnerabilities, life has persisted and adapted over 4.54 billion years of Earth's existence. The resilience of living organisms in the face of such cosmic challenges is a testament to the robustness of evolution itself, shaping the diverse ecosystems we see today. Cosmic rays from distant galaxies and our own sun constantly bombard the upper atmosphere of Earth, initiating a series of intricate processes that are both invisible to us yet essential for life on this planet. These high-energy particles, traveling at speeds close to the speed of light, interact with atmospheric molecules, creating a cascade of secondary particles. Each collision releases a burst of energy, setting off a chain reaction that can extend over distances as great as 20 kilometers. At these high altitudes, the newly formed particles contribute to the formation of aerosols, tiny droplets or clusters of molecules that act as seeds for cloud formation. The process is both microscopic and vast in its implications, with billions of collisions happening every second across Earth's atmosphere. This relentless activity underscores how cosmic events at immense scales directly influence our daily weather patterns on a minute level. What's astonishing about this phenomenon is the scale and complexity involved. Each individual collision might seem insignificant, yet collectively they form an intricate network that shapes the very clouds above us. These particles are so small that their existence can be detected only through sophisticated instruments. Despite their microscopic size, these aerosols play a pivotal role in regulating Earth's climate by influencing cloud cover and reflectivity. Clouds formed from such cosmic interactions serve multiple functions on our planet. They not only bring precipitation, but also act as shields against the sun's radiation during the day and retain heat at night, helping to maintain the average surface temperature of Earth around 15 degrees Celsius. This delicate balance is crucial for supporting liquid water and life as we know it. The journey of an aerosol particle from its initial formation in a cosmic ray collision to its eventual contribution to cloud formation reveals a fascinating story. After being created, these particles drift downward through different layers of the atmosphere, growing larger as they attract more water vapor. This process is not just about physics. It connects distant stars with the weather on Earth's surface. Scientific efforts have made significant strides in understanding this intricate process. Researchers use particle accelerators to simulate cosmic ray interactions and observe how aerosols are created under controlled conditions. These experiments provide invaluable data, helping refine climate models and predict future weather patterns more accurately. The ongoing research highlights the profound impact of cosmic events on Earth's environment, illustrating a remarkable interplay between the cosmos and our planet. In this vast cosmic ballet, each particle collision is part of an ancient process that has been shaping Earth's atmosphere for billions of years. These interactions have been occurring since long before life emerged on this blue marble, playing a role in regulating temperature and weather patterns from the very beginning. This continuity across timeframes from microseconds to eons emphasizes how interconnected our planet is with the broader universe. The particles formed from cosmic ray collisions also carry within them elements forged in ancient stars, iron, carbon, oxygen, that have been traveling through space for millions of years before interacting with Earth's atmosphere. These components are essential not only for cloud formation, but also for life itself. They highlight a profound connection between our bodies and the distant cosmos, where every element found on Earth was once part of a star's fiery death or fusion. Understanding these processes is crucial as we navigate the complexities of climate change. The delicate balance maintained by cosmic particles in our atmosphere underscores how sensitive Earth systems are to external influences. This realization invites us to consider the far-reaching consequences of human activities and their potential impacts on this intricate dance between space and our planet. This process does not just affect cloud formation, but also has implications for weather patterns across different regions. The aerosols created by cosmic rays can influence everything from local rainfall distribution to global temperature variations. In some areas, increased cloud cover due to these particles could lead to cooler temperatures, while in others, it might result in more precipitation. Each collision between a cosmic ray and an atmospheric molecule represents the release of approximately 10-15 electron volts of energy. This immense burst of energy triggers a complex series of reactions that can generate up to 1 billion secondary particles within milliseconds. These collisions are not just random events. They form part of a sophisticated system that helps regulate Earth's climate by influencing cloud cover and reflectivity. The journey of an aerosol particle is not only a tale of physics, but also one that connects the microscopic with the macroscopic world. From its formation high above Earth's surface to its eventual role in cloud formation and weather patterns, each step in this process reflects the interconnectedness of our planet with the broader universe. This intricate relationship highlights how events occurring millions of light years away can have a direct impact on life here on Earth. By studying these interactions through advanced instruments like particle accelerators, scientists gain insights into not only current weather patterns, but also future climatic changes. These experiments enable researchers to better predict the effects of cosmic rays on cloud formation and climate regulation. This knowledge is crucial for developing accurate models that can forecast environmental shifts with greater precision. Each collision between a cosmic ray and an atmospheric molecule represents a tiny, yet critical, step in maintaining Earth's delicate balance. While these events are invisible to us, they underscore the profound connection between our planet and the cosmos. This interplay is not just about weather. It also reveals the story of how elements from distant stars came together to create life on Earth. The human brain weighs about 3 pounds and contains approximately 86 billion neurons. Each neuron can form thousands of connections with other cells, allowing us to process information, experience emotions, and imagine worlds beyond our own. This intricate network operates within a space so small that it could easily fit inside an average-sized cup of coffee. Yet, this minuscule structure houses the entirety of human consciousness, the essence of who we are. In contrast, consider the universe. Vastness without end, filled with galaxies containing billions of stars and planets. The Milky Way alone has over 100 billion stars, each potentially hosting its own version of life or environments that defy our current understanding. Even so, while the cosmos spans an estimated 93 billion light-years in diameter, it is this tiny 3-pound organ that seeks to understand its place within it. Imagine standing on Earth's surface, feeling the warmth from your body radiating at approximately 37 degrees Celsius. Now envision stepping outside our planet's protective atmosphere into the near vacuum of space, where temperatures can plummet to negative 273 degrees Celsius, the point just above absolute zero. This dramatic shift highlights how fine-tuned life on Earth is for conditions that foster complexity, including consciousness. The paradox lies in the fact that while the universe offers countless environments inhospitable to complex organic systems, it also provides a single known instance where such phenomena have emerged: our planet. Our minds grapple with this cosmic scale, yet it is within this narrow band of habitability that human thought has developed and seeks meaning. Earth orbits the Sun at an average distance of about 150 million kilometers, maintaining its position in what astronomers call the habitable zone. This region allows for liquid water to persist on our planet's surface. However, beyond our solar system, there are billions more stars scattered across a galaxy that spans about 100,000 light-years in diameter. Each star could host planets, some potentially supporting life, yet we remain alone in our observations and understanding of this phenomenon. The scale at which the universe operates dwarfs even the most advanced technologies humans have developed to explore it. Despite this vastness, every human consciousness remains confined to a single planet, bound by its gravity and atmosphere. The surface temperature on Earth averages around 15 degrees Celsius, creating an environment that supports diverse forms of life. But what if we consider the extreme cold found in space? The coldest place known is not deep within interstellar voids, but rather inside laboratory equipment designed to test quantum phenomena. At temperatures just fractions above absolute zero, scientists have created conditions where atoms slow down their motion almost to a halt, revealing behaviors that challenge our conventional understanding of reality. Such extremes highlight the delicate balance Earth maintains, a planet capable of supporting life amidst a universe that fluctuates wildly between unimaginable heat and cold. This contrast underscores how precious our home is. However, it also raises an intriguing question. If Earth's conditions are so finely tuned for life, Could this be evidence that we were placed here intentionally? Earth's atmosphere, composed primarily of nitrogen and oxygen, shields us from harmful radiation while providing an essential medium for sound to travel. In space, this same air would instantly dissipate into the vacuum due to lack of pressure. Yet, despite these harsh conditions outside our protective envelope, it is within this thin layer that life has flourished in its most complex forms. Human consciousness developed here, relying on the stability and resources provided by Earth's environment. While we dream of exploring beyond our world, every thought and discovery begins from this single point, a planet among countless others, yet uniquely positioned for the emergence of self-awareness. Interestingly, while Earth appears to be a rare oasis in an otherwise inhospitable universe, some scientists speculate that life might not require such specific conditions to thrive, suggesting the possibility of alternative forms of biology based on different chemical compounds. The process of plate tectonics shapes Earth's surface through heat generated within its core. This energy drives geological activity at a rate equivalent to about 46 terawatts, enough power to light up every city on the planet thousands of times over. Yet, despite this immense energy flow, it operates at scales beyond human perception. The forces that move continents and create mountain ranges do so slowly enough for us to barely notice them in our lifetimes. In comparison, the universe churns with far greater energies, stellar explosions releasing more power than our sun emits in its entire lifetime. Yet it is on this small, dynamic stage of Earth's surface where human consciousness explores its place within the cosmos, forever seeking connections between the infinitesimal and the infinite. Imagine standing on a tectonic plate at the edge of the Pacific Ocean in Japan. Beneath your feet, the land moves imperceptibly westward toward Eurasia at about 4 centimeters per year, roughly the rate of fingernail growth. This slow drift is part of a vast, ongoing process that shapes continents and oceans over millions of years. It's hard to grasp how such a minuscule movement can eventually raise mountains or create deep ocean trenches. But these tiny motions are the architects of Earth's dynamic landscape. Each step you take on this moving platform contributes to the story of plate tectonics. This motion is powered by the heat from Earth's core, which radiates at a rate of 46 terawatts, more energy than all human-made power plants combined. The heat fuels convection currents within the mantle that push and pull these plates across Earth's surface. These forces have been active for billions of years, long before life emerged on our planet. It's humbling to consider that your feet are part of a system older than multicellular organisms. Yet, here you stand, feeling nothing more than solid ground beneath you. The Pacific Plate, the largest tectonic plate, carries islands and seamounts while moving away from its spreading ridge at speeds up to 13 centimeters per year in some regions. If we were to scale down this movement, your feet would move about as fast as a snail crosses a sidewalk. This slow pace belies the immense power behind it. In time, this drift will collide with other plates, pushing Japan and its surrounding islands further inland, reshaping coastlines and creating new mountains. The Himalayas stand as evidence of such collisions, once ocean floors, now towering peaks. The heat that drives these processes comes from residual heat left over from Earth's formation, the decay of radioactive elements within the planet's interior, and frictional heating at plate boundaries. This energy is distributed unevenly across the globe, leading to variations in temperature and pressure. In regions where plates diverge, such as along mid-ocean ridges, molten rock rises to form new crust. Conversely, where plates converge, like beneath Japan, this creates subduction zones that can lead to earthquakes and volcanic activity. These phenomena underscore how our planet's surface is a constantly evolving mosaic of geological events. Now consider the journey your body takes as you stand here. You are part of a larger system where every movement, from the smallest tremor to the grandest mountain range, is connected by deep time and thermal dynamics. Each shift in tectonic plates is like an echo through the Earth's crust, resonating with its ancient heartbeat. Your feet rest on rock that may have once been part of another continent before drifting apart millions of years ago. This plate, named for the Pacific Ocean it dominates, carries a history written in geological time, longer than human civilization has existed. To put this into perspective, while you stand here feeling stationary, your position relative to the Eurasian plate is changing. In 10,000 years, Tokyo will have shifted several kilometers westward, slowly moving closer to the continent it faces across the Sea of Japan. This journey, imperceptible day by day, is a testament to the relentless forces shaping our planet's surface over eons. As you feel the ground beneath your feet, remember that you are part of an ancient and ongoing process, standing on drifting tectonic plates, moving mountains. At a depth of 4 kilometers beneath the ocean's surface, hydrothermal vents release superheated water into the icy depths. Temperatures can soar to over 350 degrees Celsius here, while the surrounding seawater hovers around 1 degree above freezing. These vents are islands of warmth in an otherwise frigid realm. Remarkably, these vents host entire ecosystems that thrive without sunlight, instead drawing energy from chemical reactions within the Earth's crust. The paradox lies in how life can flourish amidst such extremes, heat and cold locked in eternal proximity. Each vent functions as a miniature factory, converting chemicals into biomass through processes far more ancient than photosynthesis. The water expelled by these vents carries dissolved minerals like iron and sulfur, which precipitate out as the hot fluid mixes with the cold seawater. This interaction forms towering chimneys of mineral deposits that can reach heights of over 60 meters. These structures are both fragile and enduring. They grow incrementally, but collapse under their own weight or through seismic activity. The vents themselves are powered by the slow churning of Earth's mantle, which generates heat at a rate of 46 terawatts, enough energy to power every city on our planet for an eternity. Yet, these vents exist in isolation, deep within the ocean's silent embrace, where light never penetrates and no wind stirs the waters above. In this alien environment, life has adapted not only to survive, but also to thrive. Tube worms, giant clams, and blind shrimp populate the vent communities, drawing sustenance from bacteria that convert chemicals into organic matter. These organisms are part of a food web that operates in complete darkness, sustained by chemical energy rather than sunlight. The iron-rich water emitted from these vents contributes to the formation of vast ore deposits on the ocean floor, mineral resources that will one day fuel human exploration and exploitation of deep-sea environments. It is both ironic and humbling to consider that life thrives at such depths while humans remain confined to the surface. Yet it is our insatiable curiosity about these hidden worlds that drives us deeper into the unknown. The vents themselves are part of a larger geological process known as seafloor spreading. As tectonic plates drift apart, molten rock rises from Earth's mantle and solidifies on the ocean floor. This slow but steady movement is responsible for creating new crust at rates measured in centimeters per year, about the rate at which fingernails grow. Over billions of years, this process has shaped the planet's surface, contributing to its unique geologic history. Each vent represents a fleeting moment in an ongoing saga of planetary evolution, a testament to the dynamic nature of our Earth. While individual vents may exist for only thousands of years before collapsing or being buried by sediment, their cumulative effect spans eons and shapes the very fabric of our planet. One might wonder how such extreme environments could support life at all. The answer lies in the adaptability of biological systems. Microorganisms living near these vents have evolved to withstand conditions that would be lethal elsewhere: extreme temperatures, high pressure, and toxic chemicals. These microbes form the base of an ecosystem that is both alien yet remarkably similar to terrestrial ones. In essence, they represent a parallel biosphere operating under radically different rules. This raises profound questions about life's potential beyond Earth. Could other worlds harbor similarly resilient organisms thriving in extreme environments? The hydrothermal vents are living laboratories, offering insights into the limits of life and its ability to adapt to improbable circumstances. While human exploration of these deep-sea ecosystems is still in its infancy, technological advancements have made it possible for us to observe and study them with unprecedented detail. Submersibles equipped with cameras can now venture into these abyssal realms, capturing images that would have been unimaginable just decades ago. Yet, despite our growing understanding, there remains much to discover. Vent communities continue to surprise researchers with their complexity and resilience. In the early days of our planet, 4 billion years ago, Earth was a vastly different place. Temperatures often exceeded 200 degrees Celsius, and the atmosphere was thick with noxious gases like carbon dioxide and methane. Yet, amidst these extreme conditions, microscopic organisms found ways to survive and thrive. These ancient microbes flourished in volcanic vents deep within our oceans, where temperatures soared above 300 degrees Celsius. The immense pressure from the ocean's depth created a shield against the harsher surface conditions, allowing these hardy organisms to adapt and evolve. Unlike later life forms that relied on sunlight for energy, these microorganisms harnessed chemical reactions with minerals like iron and sulfur found in vent water through chemosynthesis. This process was crucial for creating self-sustaining ecosystems before photosynthesis had even developed. The resilience of these microbes is remarkable when we consider their role in shaping the future trajectory of life on Earth. These organisms not only survived, but also played a pivotal part in altering the planet's atmospheric composition, ultimately paving the way for more complex life forms to emerge. For instance, cyanobacteria, descendants of these early chemosynthetic bacteria, eventually produced oxygen through photosynthesis, fundamentally changing our atmosphere's makeup. These ancient microbes developed sophisticated survival strategies suited to their extreme environment. They formed biofilms, communities of microorganisms adhering to surfaces, which provided protection against harsh conditions and facilitated nutrient exchange among different species. This early form of symbiosis laid the groundwork for complex ecosystems that now dominate Earth's landscapes. The ability of these organisms to cooperate in such challenging settings is a testament to their adaptability. The conditions under which these microbes thrived were uniquely conducive to life, making them incredibly rare across our solar system and beyond. The presence of liquid water, suitable chemical compounds, and stable geological activity created an environment perfectly suited for the emergence of life on Earth. This raises intriguing questions about the potential for life elsewhere in the universe, where similar conditions might exist or have existed at some point. Understanding how these early microbes adapted to such harsh environments provides valuable insights into both the origins and possibilities of life. Their resilience suggests that life can take root and flourish even in conditions we consider uninhabitable. This thought challenges our understanding of what is possible for life, pushing the boundaries of what we might discover beyond Earth's borders. These ancient organisms not only survived, but also set the stage for the diverse ecosystems we see today on land and in the oceans, highlighting the profound adaptability of life itself. In addition to their survival strategies, these microbes played a crucial role in shaping the chemical composition of early Earth's oceans. They helped regulate the levels of key elements like iron and sulfur, which are essential for biological processes. This regulation was vital for maintaining an environment that could support more complex forms of life over time. Furthermore, these ancient organisms contributed to the formation of biominerals, mineral structures created by living organisms. These minerals provided structural support and protection against predators and environmental stressors. The study of such biominerals offers insights into how early life interacted with its environment and adapted over millions of years. This interaction between biology and geology is a key factor in understanding the evolution of Earth's ecosystems. The survival strategies employed by these ancient microbes highlight their ability to thrive under conditions that would be lethal for most modern organisms. Their capacity to use chemosynthesis as an energy source demonstrates how life can find ways to exploit even the harshest environments. This adaptability suggests that life might exist in similarly extreme conditions elsewhere in the universe, challenging our assumptions about where and how life could develop. These early microbes also played a role in shaping Earth's crust through their interactions with rocks and minerals. By breaking down certain compounds and releasing others. They influenced the chemical composition of the ocean floor and contributed to the formation of sedimentary layers. This process not only helped create habitats for other organisms, but also left behind geological evidence that scientists can study today to understand the early history of life on Earth. The adaptability of these ancient microbes underscores their importance in setting the stage for more complex life forms. Their ability to thrive under extreme conditions and interact with their environment laid the groundwork for the diverse ecosystems we see today. This legacy continues to influence scientific research, offering clues about how life might have originated and evolved on other planets or moons within our solar system and beyond. Gravitational waves are ripples in the fabric of space-time caused by some of the universe's most violent events, collisions between black holes or neutron stars, for instance. These disturbances propagate through the cosmos at the speed of light, but they are incredibly faint and difficult to detect. Consider these waves as tiny distortions that stretch and compress space itself. A typical gravitational wave causes a distance of 1 mile to change by less than the width of an atom, approximately 1021 meters. This minute effect is what allows scientists at observatories like LIGO to detect these phenomena. These waves carry information about distant cosmic events, traveling across distances measured in light years. What's remarkable about gravitational waves is their ability to reveal otherwise invisible cosmic occurrences. For example, a collision between two black holes can produce detectable gravitational waves on Earth, even though it happened millions of light years away. This interaction not only tells us about the event itself, but also about the physics operating in extreme conditions, such as near or beyond the speed of light. The LIGO detectors use laser interferometry to measure these minute distortions. When a gravitational wave passes through, it causes the length of two perpendicular arms to change by an infinitesimal amount, smaller than 1/10,000th the diameter of a proton. This precision allows researchers to confirm theories and explore new ones in the realm of space-time dynamics. The technology behind LIGO is so advanced that it can detect changes far smaller than any human could perceive. Gravitational waves connect us not just with distant cosmic occurrences, but also with the origins of time itself. Some scientists speculate that these ripples might carry imprints from the Big Bang, providing clues about the universe's infancy and its grand design. Each detection is like a snapshot from an ancient cosmic history book, written in the language of space-time ripples. Gravitational wave detectors are not just instruments. They are windows into the universe's past, present, and future. They allow us to witness events that occurred before our solar system existed or will occur long after it ceases to be. Each detection provides new data points for calibrating models and theories about black holes, neutron stars, and other exotic objects. This continuous accumulation of knowledge reshapes how scientists interpret the universe's structure and evolution. Imagine a future where gravitational waves are used to map out vast regions of space-time in unprecedented detail. We could potentially trace the formation of galaxies, observe the merging of supermassive black holes, or even detect ripples from cosmic strings, hypothetical one-dimensional defects left over from the Big Bang. This level of precision would allow us to explore the universe's infancy and its grand design. Gravitational waves also offer insights into the behavior of space-time under extreme conditions. For instance, they challenge our understanding of how black holes merge and what happens when their horizons collide. These events can create shockwaves that travel through space-time at the speed of light, momentarily distorting it in ways predicted by general relativity, but never before observed. The precision required to detect these waves is remarkable. LIGO's mirrors are so stable that they would need to be moved only a fraction of an atom's width for us to notice. This level of control and accuracy pushes the boundaries of what we thought possible in experimental physics. It also highlights the meticulous work behind each detection, where every detail counts. For instance, even tiny seismic movements on Earth can interfere with LIGO's measurements, requiring extensive isolation techniques to ensure data integrity. In essence, gravitational wave detectors are not just passive observers, but active participants in unraveling the universe's mysteries. They enable scientists to test predictions from Einstein's theory of relativity under conditions that could not be replicated on Earth, providing evidence for phenomena that were once purely theoretical. Each detection is a step towards understanding the true nature of space-time and its role in shaping the cosmos. Solar flares are eruptions of energy from the sun's surface that can release more energy in a single event than humanity has used since the dawn of civilization. These bursts, often lasting just minutes or hours, send out electromagnetic radiation and particles at near-light speed. When they reach Earth, they interact with our planet's magnetic field, causing geomagnetic storms. These storms can interfere with satellite communications and power grids, sometimes leading to widespread disruptions on Earth. The effects of solar flares are not confined to the present. They leave a historical record in Earth's geology. Magnetic minerals in ocean floor sediments align with the Earth's magnetic poles as they shift over time. Scientists study these patterns to understand past solar activity and its impact on our planet's history, revealing how ancient flares have influenced geological processes. Modern technology is not immune to these cosmic events. Satellites, which rely on precise timing signals for their operations, can experience glitches or failures during geomagnetic storms. A single malfunctioning satellite can trigger a cascade of issues affecting entire networks, underscoring the interconnectedness of our technological systems. The sun's influence extends far beyond just providing light and warmth. It shapes Earth's environment in ways that are both subtle and dramatic. For instance, solar flares can strip away some of Earth's upper atmosphere, leading to changes in atmospheric composition over time. This process highlights how the sun is a constant yet dynamic force in our lives. Understanding these phenomena requires sophisticated models and observations. Solar observatories continuously monitor the sun for signs of flare activity, using data from space-based telescopes. Despite this technology, Predicting the exact magnitude of an upcoming solar event remains challenging, as each one can be unique in its intensity and effects on Earth systems. The energy released during a major solar flare is equivalent to thousands of nuclear explosions combined. This immense power can cause electromagnetic radiation to reach Earth within minutes, disrupting satellite operations and even affecting GPS signals. The intensity of these events varies greatly. Some are so powerful they can be detected across the entire electromagnetic spectrum, from radio waves to gamma rays. Humans on Earth do not typically experience direct physical harm from solar flares due to the protective layers of our atmosphere and magnetic field. However, astronauts in low Earth orbit or during spacewalks face a greater risk. They are exposed to higher levels of radiation that can increase their chances of developing cancer over time if they spend extended periods outside the protection of Earth's magnetosphere. The frequency of solar flares is tied to the Sun's 11-year activity cycle, known as the solar maximum and minimum. During peak activity, the Sun produces more sunspots, which are regions where magnetic fields become concentrated and often lead to flare events. This cyclic behavior has been observed for centuries, but remains a subject of ongoing research to better predict when major flares might occur. Looking far into the future, our understanding of solar flares could have implications for interstellar travel if humanity ever ventures beyond Earth's orbit. Spacecraft traveling through deep space would need robust shielding to protect against such high-energy events. The design of these vessels must account not only for the immediate dangers, but also for the long-term effects on crew health and mission success, ensuring safe passage through unpredictable cosmic weather conditions. Beneath the layers of modern Earth's oxygen-rich atmosphere lies a forgotten world where microbial life thrived without breathable air. This era, extending from around 4 to 2 billion years ago, was dominated by anaerobic bacteria that shaped our planet's early history. At this time, Earth's surface temperature averaged around 80 degrees Celsius, far hotter than today's 15 degrees Celsius. Despite these scorching conditions, microbial life found ways to thrive, especially in the oceans where temperatures were more moderate and suitable for survival. These ancient organisms did not rely on sunlight like modern plants, but instead engaged in chemosynthesis, converting simple compounds and minerals into energy. One significant group was cyanobacteria, which would later play a crucial role in oxygenating our planet's atmosphere. Microbial life was incredibly diverse, with some species thriving in hydrothermal vents deep within the ocean. These vent communities are isolated from sunlight, but teem with life sustained by chemical energy sources like hydrogen sulfide and methane. The pressure at these depths can reach over 400 atmospheres, a condition that would crush a human body instantly if exposed unprotected. Remarkably, these organisms have adapted to thrive in such extreme environments, showcasing the resilience of early Earth's inhabitants. The process by which these early organisms adapted to survive without oxygen is fascinating when compared to modern ecosystems. In today's world, oxygen plays a critical role in most metabolic processes, Yet for billions of years, Earth supported complex communities entirely devoid of it. This paradox highlights the flexibility and adaptability of life forms on our planet. The absence of oxygen meant that these organisms had to evolve unique strategies for energy production and waste management. One particularly intriguing aspect is how these ancient microbes influenced Earth's geology over time. Microbial processes helped in the formation of certain mineral deposits, contributing to the rich geological record we study today. For instance, some bacteria were involved in the precipitation of iron oxides, creating vast deposits that would later be mined for their valuable metal content. This symbiotic relationship between early life and Earth's geology underscores how closely intertwined biological processes can be with planetary evolution. Understanding these ancient microbial ecosystems provides valuable insights into how life might exist on other planets with different atmospheric compositions. The resilience and adaptability demonstrated by early Earth's inhabitants suggest that life forms elsewhere in the universe could similarly thrive under conditions vastly different from our own. For example, extremophiles found on Earth can survive temperatures up to 120 degrees Celsius or pressures exceeding 10,000 atmospheres, indicating potential for extraterrestrial life to exist in environments with similar extremes. The transition from an anaerobic planet to one rich with oxygen was a gradual process taking millions of years. During this time, cyanobacteria steadily increased the concentration of atmospheric oxygen through their photosynthetic activities. This rise in oxygen levels allowed for the development of more complex organisms that could harness this newfound resource for energy production. However, it also introduced challenges such as reactive oxygen species that could damage biological molecules if not properly managed. These early organisms were not only crucial for shaping Earth's atmosphere, but also played a significant role in regulating its climate. By fixing carbon dioxide and producing methane, they helped maintain the planet's temperature within a range suitable for life. This delicate balance allowed for the emergence of more complex ecosystems as oxygen levels increased, setting the stage for the diverse biosphere we see today. In these ancient conditions, microbial organisms played a crucial role in regulating Earth's chemical cycles. They helped fix nitrogen from the atmosphere into compounds useful for other life forms and contributed to the formation of important minerals through biomediated processes. This unseen work laid the groundwork for more complex ecosystems that would eventually develop as oxygen levels increased. Each microbial species on early Earth had a specific role in maintaining the planet's delicate balance. Some bacteria were responsible for breaking down organic matter, while others helped recycle nutrients back into the environment. This intricate web of interactions demonstrates how life can thrive even without the presence of oxygen, highlighting the versatility and adaptability of biological systems. Imagine standing on a continent as it slowly shifts across Earth's surface, moving at an imperceptible pace of about 4 centimeters each year, less than 2 inches. This movement is driven by forces deep within our planet, where temperatures exceed 3,000 degrees Celsius and pressures crush rock into plasticity. Each plate tectonic event reshapes not just mountains, but entire coastlines over geological epochs. In contrast to the rapid shifts we might observe in human lifetimes, these processes unfold across millennia, with each movement a mere fraction of an inch per year. Plate tectonics has sculpted Earth's surface into diverse landscapes through gradual pressure and collision. Mountains like the Himalayas are still growing taller as India continues its inexorable collision with Asia at a rate of about 20 millimeters annually. This gradual pressure can generate forces strong enough to lift rock thousands of meters into the air, turning ancient sea floors into towering peaks. Consider this. If you were to stand atop one of these rising mountains and look back through time by 10 million years, your view would have been vastly different. The landscape would be lower, flatter, and more akin to an ocean floor than a mountain range. This geological time perspective is a reminder of how fleeting human lifespans are in comparison. Plate tectonics also shapes the boundaries between land and sea by pushing up coastal ranges or pulling apart continents to create ocean basins. The Mid-Atlantic Ridge exemplifies this process, where new seafloor continuously forms as magma rises from deep within the Earth's mantle and cools into rock. This continuous creation of new crust means that some parts of the Atlantic Ocean floor are no older than 20 million years. In a cosmic context, this is almost instantaneous geological activity. The movement of tectonic plates influences global climate patterns through their interaction with atmospheric systems. As continents drift, they can block ocean currents or open up channels that allow warm waters to circulate poleward, affecting weather on opposite sides of the globe. The shifting position of land masses over millions of years can cause ice ages or periods of increased volcanic activity, both critical factors in shaping life's evolution. For instance, when Africa and South America separated some 150 million years ago, it altered oceanic and atmospheric circulation patterns that affected global climate for eons. Plate tectonics plays a crucial role in recycling Earth's surface materials. As one plate sinks beneath another into the mantle, it undergoes extreme heat and pressure, transforming rock into different compositions. Some of these rocks eventually rise back to the surface through volcanic activity, completing a cycle that recycles elements across geological epochs. This process ensures that the planet remains chemically active and capable of supporting life for billions more years. Imagine if Earth's crust were entirely static. Without this constant renewal, its composition might become too depleted in vital minerals essential for life. Finally, plate tectonics has been at work since the dawn of planet formation itself, shaping early continents 4 billion years ago as Earth cooled from its fiery birth state. These initial landmasses were much smaller and more unstable than those we see today, constantly breaking apart and reforming through collisions and separations driven by internal heat flow. Over time, these processes have smoothed out many of the original irregularities on Earth's surface, creating a balance that allows for diverse ecosystems to flourish across different climates and terrains. This long history underscores how integral plate tectonics is to our planet's ongoing ability to support life in all its forms. Infrasound waves ripple through the ground during an earthquake, traveling at speeds exceeding 5 kilometers per second, faster than sound in air. These vibrations carry information about the source of seismic activity, allowing geologists to pinpoint where an earthquake originated with remarkable precision. This speed and accuracy are crucial for understanding how tectonic forces reshape our planet over millions of years. When a volcanic eruption occurs near coastal areas, the infrasound generated can travel across water bodies, sometimes even crossing entire continents before dissipating. For example, the explosion from Mount St. Helens in Washington state was detected as far away as Australia, illustrating how events on one side of the planet can have repercussions on the other. This long-distance transmission highlights the global interconnectedness of Earth systems. Infrasound also plays a role in monitoring extreme weather phenomena like hurricanes and tornadoes. These powerful atmospheric disturbances generate low-frequency sounds that infrasonic microphones can detect from great distances. By analyzing these signals, meteorologists gain valuable information about the intensity and movement of storms before they make landfall. This early warning system helps communities prepare for potential hazards, underscoring the practical applications of studying infrasound. Interestingly, the study of infrasound extends beyond Earth to other celestial bodies within our solar system. The Huygens probe detected low-frequency signals on Saturn's moon Titan during its descent through the thick atmosphere in 2005. These sounds provided valuable data about wind patterns and atmospheric composition on this distant world. Infrasound thus serves as a tool for exploring environments far beyond our own planet, offering glimpses into alien worlds that would otherwise remain unknown. In contrast to the solid ground of earthquakes or the fluid dynamics of weather systems, infrasound can also reveal the hidden activity beneath ice sheets and glaciers. For instance, researchers have used infrasonic microphones to detect the movement of icebergs carving from glaciers. These low-frequency sounds provide insights into glacial processes that are otherwise difficult to observe directly. This application highlights how infrasound can be a versatile tool in understanding diverse environmental phenomena. By studying infrasound, we gain deeper insights into Earth's dynamic nature and its enduring power to shape both landscapes and lives. These low-frequency vibrations offer tangible evidence of hidden forces within our planet, transforming geological processes into something perceivable. While we cannot hear these sounds directly, their study illuminates the intricate web of forces that shape our world and its place within the cosmos. Infrasound also reveals the subtle rhythms of volcanic activity deep beneath Earth's surface. As magma moves through underground chambers, it generates low-frequency vibrations that can be detected by sensitive equipment on the surface. These signals provide geologists with a window into the inner workings of volcano, allowing them to monitor changes in pressure and composition before an eruption occurs. This capability is particularly valuable for predicting volcanic activity, which can have devastating consequences if not adequately prepared for. For instance, infrasound monitoring played a crucial role during the 2018 eruption of Kilauea volcano on Hawaii's Big Island. By analyzing the low-frequency sounds generated by the volcano, scientists were able to track shifts in magma movement and pressure changes within the volcanic system. This information helped authorities issue timely warnings to local residents, ensuring their safety as lava flows encroached upon populated areas. The ability of infrasound to provide early warning signals underscores its importance in mitigating the risks associated with natural disasters. The study of infrasound also extends beyond immediate hazard assessment to include long-term environmental monitoring. By continuously tracking low-frequency vibrations, researchers can gather data on tectonic plate movements and volcanic activity over extended periods. This information contributes to our understanding of Earth's geological history and helps refine models predicting future seismic events. Infrasound thus bridges the gap between short-term crisis management and long-term scientific inquiry, offering a comprehensive view of how our planet evolves. In addition to its practical applications in disaster preparedness and environmental monitoring, infrasound provides unique insights into the acoustic properties of different materials within Earth's crust. For example, the speed at which infrasonic waves travel through rock or sediment can reveal information about the composition and density of these materials. This knowledge aids geologists in mapping subsurface structures and identifying potential mineral deposits. Infrasound, therefore, serves as a powerful tool for exploring both the immediate dangers and long-term resources hidden beneath our feet. By delving into the world of infra, water moves through Earth systems in a continuous cycle, endlessly transforming from vapor to liquid and back again. A single water molecule might spend years locked away deep underground before reappearing as raindrops or river ripples. This journey begins when evaporation carries water vapor into the sky, where it cools and condenses into clouds. Each cloud droplet is born from countless microscopic collisions of water molecules, forming a delicate structure that floats on air currents. Clouds are not static. They drift and merge, grow larger or disperse, depending on temperature and humidity. Yet, for all their dynamism, the total amount of water vapor in Earth's atmosphere remains remarkably constant, about 12,900 cubic kilometers at any given time. This stability is crucial because it ensures that life can rely on predictable patterns of rainfall and drought. In a paradoxical twist, the most abundant form of liquid water we see today is actually stored far below our feet in underground aquifers, invisible to the naked eye. Water seeps into porous rock layers through tiny fractures and crevices, forming vast reservoirs deep beneath Earth's surface. These aquifers hold an estimated 23 million cubic kilometers of fresh water, about 30 times more than all the rivers and lakes combined. Yet only a fraction is accessible for human use, hidden away in spaces between grains of sand or cracks in bedrock. This subterranean world remains largely unexplored, its depths guarded by ancient layers of sedimentary rock. The pressure down there can reach hundreds of atmospheres, squeezing water tightly into the smallest openings. As underground aquifers feed rivers and lakes, they also influence geological processes deep within Earth's crust. Water acts as a lubricant for tectonic plates, reducing friction between them and helping to shape mountain ranges over millions of years. In some areas, such as California's San Andreas Fault, groundwater can weaken rock structures, increasing the likelihood of earthquakes. This connection highlights how deeply intertwined life on our planet is with geological processes. Without water cycling through Earth systems, many familiar landscapes would never have formed. During heavy rainfall, water rushes down hillsides and into rivers, eroding soil along the way. Each drop carries tiny particles of sediment that accumulate in riverbeds and deltas, gradually building up layers of mud and silt over centuries. This process not only shapes river channels, but also enriches coastal plains with nutrient-rich deposits. In contrast to the slow, steady flow of underground aquifers, rivers can change course dramatically within a single season due to flooding or shifting sandbars. The Mississippi River alone transports an estimated 437 million metric tons of sediment into the Gulf of Mexico each year. Water's journey from cloud to river is not just about moving physical matter, it's also a conveyor belt for life. Rivers and lakes are home to countless species, from microscopic plankton to giant fish like sturgeon, which can live over a century. These aquatic ecosystems thrive in part because water circulates nutrients between different environments. For instance, rain falling on forests provides essential elements that nourish plants, while runoff delivers those same nutrients downstream where they support aquatic life. This interconnectedness underscores the delicate balance maintained by Earth's water cycle. Objects in space do not float because they are weightless. Rather, they are continuously falling towards Earth, but moving so fast that they never hit it. This phenomenon is known as microgravity, where objects appear to drift freely due to their constant free fall around our planet. An astronaut floating inside the International Space Station experiences this sensation, with every item aboard following a similar path. Consider an object like a pen in space. It does not defy gravity. Instead, it is in a state of perpetual free fall alongside its surroundings. This environment creates a unique illusion where objects seem weightless, yet they are still subject to the gravitational pull of Earth. The ISS orbits at approximately 400 kilometers above the surface, traveling at speeds exceeding 27,000 kilometers per hour, fast enough to maintain this orbit without falling back into the atmosphere. In microgravity, time itself behaves differently. Atomic clocks on satellites run slightly faster than those on Earth due to a phenomenon known as gravitational time dilation. This effect is predicted by Einstein's theory of general relativity and demonstrates how gravity influences not just space, but also time. For astronauts aboard the ISS, this means their perception of time aligns more closely with that experienced far from Earth's surface. Microgravity affects biological processes in unexpected ways. On Earth, blood tends to pool at the lower half of the body due to gravity. In space, however, fluids distribute more evenly throughout the body, leading astronauts to experience a sensation similar to having a head cold. This fluid shift can cause puffy faces and constricted veins, altering how their bodies function in this unique environment. Materials behave differently under microgravity conditions as well. For instance, metal alloys can be processed into shapes that would otherwise be impossible on Earth due to the absence of gravitational effects pulling them out of shape. This opens up possibilities for manufacturing intricate components with precision unattainable through traditional methods here on our planet. While objects float in space due to microgravity, this phenomenon is a product of continuous acceleration toward Earth. This paradoxical state challenges our understanding of gravity, revealing its dual nature, both as a constant force pulling objects toward Earth and as an environment where free-floating movement can occur. This duality underscores the intricate relationship between gravity and motion, offering insights into the fundamental physics that govern our universe's behavior both near and far from Earth. In microgravity, even simple actions like drinking water become an intricate process. Without gravity to pull liquid downward, astronauts must use specialized bags with straws designed to counteract surface tension and capillary action. Water droplets form perfect spheres in space, floating freely until they are consumed or coalesce into larger drops. This behavior is not just a curiosity, but a fundamental aspect of how liquids interact in environments where traditional gravitational forces do not dominate. The absence of gravity also affects the way sound travels, or rather, doesn't travel, onboard spacecraft. Sound waves require a medium like air to propagate, and in the vacuum of space, there is none. This means that conversations between astronauts inside the ISS are conducted through radio communication systems, as sound cannot carry across the void between them. Yet within the pressurized confines of the station, sound behaves normally due to the presence of breathable air, illustrating how environments can be carefully engineered to support human life despite the harshness of space. Microgravity impacts not only physical phenomena, but also biological processes on a cellular level. Muscle atrophy and bone density loss are common issues faced by astronauts during prolonged stays in orbit. In Earth's gravity, muscles constantly work against resistance, maintaining their strength and size. However, in microgravity, this constant exertion is absent, leading to muscle fibers breaking down over time. To counteract these effects, astronauts engage in rigorous exercise routines using specialized equipment designed for use in space. This unique environment also presents challenges for waste management systems aboard spacecraft. Traditional plumbing relies on gravity to direct liquid and solid waste through pipes. In microgravity, alternative methods are required to ensure proper disposal of waste products. Engineers have developed systems that rely on centrifugal force or air pressure to move waste materials through the system, ensuring a clean and hygienic environment for astronauts during their missions. Understanding these effects is crucial not only for current space operations, but also for future long-duration missions beyond low Earth orbit, as humanity looks toward destinations like Mars. Earth rotates on its axis once every 24 hours, creating the familiar day-night cycle that shapes life as we know it. This rotation is not uniform. Points near the equator move at speeds of about 1670 kilometers per hour, while regions closer to the poles experience significantly slower rotational velocities. The centrifugal force generated by this spin contributes to Earth's slightly oblate shape, slightly flattened at the poles and bulging at the equator. The planet's axial tilt, approximately 23.5 degrees relative to its orbital plane, is responsible for seasonal variations. As Earth orbits the Sun, different hemispheres receive varying amounts of sunlight, leading to distinct seasons. This tilt also influences how stars appear in our night sky, causing constellations to shift throughout the year as we rotate on our axis. Interestingly, this axial tilt is not constant. It wobbles slightly over thousands of years, a phenomenon known as precession. Humans have evolved circadian rhythms, internal biological clocks, that synchronize with this day-night cycle. These rhythms regulate sleep patterns, hormone production, and other physiological processes. However, astronauts aboard the International Space Station experience 16 sunrises and sunsets every 24 hours due to their rapid orbit around Earth. This disruption of natural cycles can lead to sleep disorders, demonstrating how sensitive our bodies are to regular day-night rhythms. The human body's reliance on this cycle is so profound that even brief disruptions can affect cognitive function and mood. Earth's rotation plays a crucial role in shaping global weather patterns through differential heating between day and night. During the day, sunlight heats the surface, causing air to rise and creating conditions for cloud formation and precipitation. At night, cooler temperatures cause air to sink, leading to clear skies and calmer winds. This cycle drives the water cycle, from evaporation to condensation and eventual rainfall. The Coriolis effect, caused by Earth's rotation, also influences wind patterns, guiding them in specific directions. Other planets in our solar system have vastly different rotational periods compared to Earth. Mars rotates slightly slower, taking about 24.5 hours per sol. In contrast, Venus has an extremely slow rotation period of 243 Earth days. These variations in rotation rate affect the length of day, temperature extremes, and atmospheric dynamics on each planet. For instance, Venus's thick atmosphere and slow rotation contribute to surface temperatures that can reach over 460 degrees Celsius. Earth's rotation also affects weather patterns by influencing the speed at which air masses move across its surface. The faster a region rotates, the more rapidly air moves, leading to stronger winds. This phenomenon is particularly noticeable near the equator, where high-speed winds contribute to powerful storms like hurricanes. In contrast, areas closer to the poles experience slower-moving air and generally calmer weather conditions. Understanding Earth's spin is essential for comprehending various aspects of planetary science, from climate patterns to geological processes. The precise measurement of this rotation, down to fractions of a millimeter per second, is made possible by advanced geodetic techniques and satellite observations. This knowledge not only aids in accurate timekeeping, but also deepens our understanding of how Earth's dynamic systems interact with each other over time. It allows us to predict tides, study plate tectonics, and even model the long-term effects of climate change on our planet. The day-night cycle also influences the behavior of countless species across the globe. Many animals have adapted to be primarily active during either daylight or nighttime hours, a phenomenon known as diurnal and nocturnal activity patterns. For example, owls are well suited for night hunting due to their exceptional vision and hearing, which allow them to navigate and hunt effectively in low-light conditions. Conversely, bees rely on sunlight to locate flowers and perform their vital role of pollination during the day. These adaptations highlight how life has evolved in harmony with Earth's rotation, optimizing survival strategies based on available resources at different times. Earth's spin not only affects the surface, but also influences the dynamics of its atmosphere and oceans. As the planet rotates, it creates a Coriolis effect that deflects moving air masses to the right in the northern hemisphere and to the left in the southern hemisphere. This deflection plays a key role in shaping global wind patterns and ocean currents. For example, the Gulf Stream carries warm water from the equator towards northern regions of the Atlantic Ocean, significantly influencing weather systems along its path. The rotation also impacts the distribution of heat across Earth's surface. During the day, sunlight warms different parts of the planet unevenly due to variations in land and sea coverage. Land heats up more quickly than water, leading to temperature differences between continents and oceans. These disparities drive wind patterns and ocean currents that redistribute heat around the globe, helping to at the boundary where Earth's atmosphere meets the vacuum of space, a thin layer known as the thermosphere stretches no more than a few hundred kilometers above our heads. Here, temperatures can reach up to 1300 degrees Celsius due to the absorption of high-energy solar radiation by oxygen atoms. The pressure is so low that it would feel like being at the summit of Mount Everest, but with air molecules sparse and widely spaced. This layer acts as a crucial barrier, shielding Earth from the harsh realities of space. Without this thin shield, life on our planet would be impossible due to extreme temperature fluctuations and radiation. At approximately 100 kilometers above sea level, satellites orbit in what we call low Earth orbit. These artificial objects experience continuous exposure to cosmic radiation and micrometeoroids, yet they remain operational due to careful engineering. The thinness of the thermosphere is paradoxical. It's both fragile and vital for life on Earth. Despite its fragility, this layer manages to protect us from harmful solar winds and high-energy particles that could otherwise strip away our atmosphere. Interestingly, the density of air in this region is so low that a feather dropped here would fall as fast as a hammer due to the lack of aerodynamic drag. Atmospheric gases gradually thin out as altitude increases, transitioning into the vacuum of space. This transition zone is where auroras form, beautiful light displays caused by charged particles from the sun interacting with atmospheric molecules. These phenomena are visible primarily at high latitudes, where the magnetic field funnels these particles toward the poles. The energy released in this process can heat the upper atmosphere, causing it to expand and contract. This expansion and contraction of the thermosphere is influenced by solar activity, which varies on an 11-year cycle known as the solar maximum. Despite its extreme temperatures, the thermosphere plays a critical role in maintaining Earth's climate balance. The layer absorbs much of the sun's ultraviolet radiation, preventing it from reaching the surface and causing more severe heating. This absorption process also contributes to the ionization of gases within the atmosphere, creating a region rich in charged particles known as the ionosphere. These ions can reflect radio waves, enabling long-distance communication and navigation systems that rely on signals bouncing off this layer. The magnetic field generated by Earth's liquid outer core plays a vital role at this boundary, protecting us from cosmic radiation and solar winds with a strength of around 25 to 65 microteslas at the surface. This invisible shield deflects charged particles away from our planet, preserving the integrity of the atmosphere below. The magnetic field also influences the behavior of auroras by guiding the flow of energetic particles that cause these spectacular light shows. Without this protective barrier, life on Earth would be exposed to harmful radiation levels far exceeding those found in deep space. This thin layer is not only vital for life's survival, but also serves as a crucial platform for human exploration and technology. Satellites orbiting within the thermosphere are essential for communication, weather monitoring, and scientific research. The International Space Station operates at an altitude of about 408 kilometers, well within this fragile region. Astronauts aboard the ISS must wear spacesuits to protect themselves from the extreme conditions outside their spacecraft. These suits provide a pressurized environment that mimics Earth's atmosphere, allowing humans to survive in the vacuum of space. The thermosphere thus stands as both a boundary and a bridge between our planet and the cosmos beyond. Beyond Earth's magnetic shield, cosmic radiation presents a formidable challenge to human physiology. In the vacuum of space, each square meter absorbs an estimated 13 rem per day due to galactic cosmic rays and solar particle events. This is nearly 50 times more than the annual limit recommended for nuclear plant workers on Earth. The body's cells react to this bombardment by attempting to repair damaged DNA, but the sheer volume of radiation can overwhelm these mechanisms. Within hours of exposure, an astronaut might experience nausea, fatigue, and a drop in white blood cell count, symptoms akin to severe influenza. Yet, paradoxically, it is not the immediate effects that pose the gravest threat. Rather, it's the long-term risk of cancer and genetic mutations that may only manifest decades later. Earth's magnetic field, generated by our planet's molten iron core, deflects these harmful particles away from us with a strength of about 25 to 65 microteslas at the surface. This thin layer acts like an invisible shield, protecting all life on Earth from the relentless cosmic radiation. However, this protective bubble is not uniform. It has weak points called magnetic cusps, where high-energy particles can enter more easily. Spacesuits provide limited protection against radiation, but are far from foolproof. They incorporate layers of material designed to absorb or scatter incoming particles, such as mylar and Kevlar fabrics. Yet, even with these measures, the risk remains significant for extended space missions. The International Space Station orbits within Earth's magnetic field, providing some shielding, yet astronauts still experience a higher radiation dose than people on the ground. Radiation exposure in space also affects spacecraft electronics, causing random errors in computer systems known as single-event upsets. These events can corrupt data or even crash critical systems if not properly mitigated. Engineers design robust error-checking protocols and redundant circuits to minimize these risks, but they cannot eliminate them entirely. This underscores the complexity of maintaining technological integrity in such an unforgiving environment. Despite the dangers, cosmic radiation plays a crucial role in space exploration and understanding our universe. It serves as a reminder of the delicate balance that sustains life on Earth. As we venture further into space, developing effective countermeasures against cosmic rays becomes paramount for ensuring safe human habitation beyond our planet's protective shield. This ongoing challenge continues to push the boundaries of medical science, engineering, and our understanding of how life can thrive in extreme conditions. Beyond the immediate threat to astronauts, cosmic radiation also poses a significant risk to long-term space missions. For instance, during solar storms, the sun emits vast amounts of charged particles that can damage spacecraft electronics and harm human tissue if not adequately shielded. These events are unpredictable and can occur at any time, making it essential for mission planners to account for such risks. Moreover, prolonged exposure to cosmic radiation can lead to cognitive decline in astronauts. Studies on mice exposed to high levels of radiation show a decrease in neurogenesis, the formation of new neurons, and an increase in inflammation within the brain. This could potentially impair decision-making and memory functions in humans during extended space missions. Understanding these effects is crucial for developing countermeasures, such as pharmaceuticals or enhanced shielding materials. In addition to its direct health impacts, cosmic radiation can also alter genetic material over generations. If astronauts were to establish colonies on other planets, the cumulative effect of radiation exposure could lead to mutations in future generations. These changes might not be immediately apparent, but could accumulate gradually, affecting everything from physical traits to disease susceptibility. This raises important ethical questions about long-term space exploration and its potential consequences for human evolution. To mitigate these risks, researchers are exploring various strategies, including advanced shielding technologies and genetic modifications. One promising approach involves using materials like boron nitride nanotubes, which can absorb high-energy particles more effectively than traditional metals. Additionally, Scientists are investigating ways to enhance the natural repair mechanisms within cells, potentially reducing the damage caused by cosmic radiation. Another critical aspect of addressing cosmic radiation is understanding its long-term effects on ecosystems. If humans were to colonize other planets or moons, they would need to bring along life support systems capable of sustaining complex biological processes in environments where cosmic radiation levels are much higher than on Earth. This challenge requires not only protecting individual organisms, but also ensuring the viability of entire ecosystems over time. Despite these challenges, the study of cosmic radiation offers valuable insights into fundamental aspects of physics and biology. For example, understanding how particles interact with matter at high energies can inform our knowledge of particle accelerators and nuclear reactions. Similarly, studying the effects of radiation on living organisms provides crucial information for medical research, particularly in cancer treatment and radiobiology. Furthermore, cosmic radiation plays a role in shaping planetary surfaces across the solar system. On Mars, for instance, exposure to unfiltered solar wind has eroded much of its atmosphere over billions of years, leaving behind a thin layer that offers little protection against harmful radiation. This process highlights how external forces can dramatically alter a planet's environment and underscores the importance of protecting any potential habitats from similar threats. In conclusion, while cosmic radiation presents significant challenges for human exploration beyond Earth's protective magnetic field, it also opens up new avenues for scientific discovery and innovation. By addressing these risks head-on, we may unlock deeper understandings of both our universe and ourselves. The Moon's gravitational pull on Earth stabilizes our planet's axial tilt, ensuring consistent seasons and climates over millennia. This subtle dance keeps the angle of Earth's axis relatively constant at about 23.5 degrees. Without this stability, extreme variations in climate could occur, making life as we know it far less likely to flourish. Imagine standing on a beach during high tide. The water laps gently against your feet, its rhythm dictated by the Moon's gravitational tug. This tidal influence not only shapes coastlines, but also subtly affects Earth's rotational axis. Over time, this interaction helps maintain the planet's tilt, preventing dramatic climate shifts that could otherwise disrupt ecosystems. The Moon is a stabilizing force for our planet, ensuring that Earth's axial tilt remains consistent at approximately 23.5 degrees over billions of years. This stability is maintained through gravitational interactions that create slight deformations in Earth's shape, influencing the movement of molten iron within the core. These deformations can affect the magnetic field, which protects us from cosmic radiation and solar winds. Every time you feel safe under the sky, you might unknowingly be experiencing the result of this cosmic dance. The Moon's stabilizing influence extends beyond just our planet's axis. It also plays a role in regulating tides and even influencing plate tectonics through gravitational forces. These tidal interactions can cause stress on Earth's crust, potentially triggering volcanic activity or seismic events. This subtle yet powerful effect underscores the moon's ongoing impact on our dynamic world. As you look up at night, remember that the seemingly distant celestial body is quietly shaping life here on Earth. The moon has been a constant companion to Earth for billions of years, but its influence reaches far beyond just stabilizing our planet's axis. It plays a crucial role in regulating tides and even influencing plate tectonics through gravitational forces. These tidal interactions can cause stress on Earth's crust, potentially triggering volcanic activity or seismic events. This subtle yet powerful effect underscores the moon's ongoing impact on our dynamic world. The moon's stabilizing influence extends not just to our planet, but also across generations of life. The relatively stable seasons and climates provided by this gravitational dance have allowed complex ecosystems to evolve over time. This stability has been a key factor in the development of diverse species, including humans. Over millions of years, life on Earth has adapted to these conditions, leading to intricate biological clocks that rely on predictable environmental cues. Every sunrise and sunset is a testament to the moon's stabilizing effect. The moon's influence on Earth extends even further back in time, shaping the very conditions that allowed life to emerge. Over 4 billion years ago, when Earth was a volatile place with frequent asteroid impacts and intense volcanic activity, the moon's stabilizing effect began to take hold. This gradual stabilization of the planet's axis helped create more predictable climate patterns, which were crucial for the development of early microbial life. These simple organisms thrived in environments that offered some stability amidst the chaos, setting the stage for the evolution of more complex life forms. As these ancient microbes began to flourish, they played a pivotal role in modifying Earth's atmosphere by producing oxygen through photosynthesis. This process was not instantaneous, but occurred over millions of years, gradually transforming the planet's environment. The moon's stabilizing influence on Earth's axis ensured that these changes could occur steadily without being disrupted by extreme climatic variations. This consistency provided the necessary conditions for life to evolve and diversify. The moon's role in maintaining stable seasons and climates has been a cornerstone for the development of ecosystems over time. It has allowed species to adapt to their environments, leading to the rich biodiversity we see today. Every tree that stands tall, every animal that roams freely, and every human who enjoys predictable weather patterns owes part of this stability to our celestial companion. The moon's quiet influence is a testament to its profound impact on life's journey on Earth. Solar flares are powerful bursts of energy from the sun's surface, capable of releasing more energy in a single event than humanity has used since the dawn of civilization. These eruptions can eject vast amounts of plasma and radiation into space, including high-energy particles that travel at nearly the speed of light. If such an intense solar flare were to occur and Earth were directly in its path, it could strip away our protective atmosphere over time. The average surface temperature of Earth is approximately 15 degrees Celsius, which supports liquid water and life as we know it. However, as the atmosphere thins due to repeated solar flares, this delicate balance would be disrupted. The increased exposure to cosmic radiation could lead to higher mutation rates in living organisms, potentially threatening genetic stability. Meanwhile, the temperature extremes on Earth's surface might become more pronounced, making survival increasingly difficult for many species. Earth's magnetic field, generated by its liquid outer core, acts as a shield against solar winds and cosmic radiation, deflecting harmful particles away from our planet. This field is crucial in maintaining the atmospheric conditions necessary for life. Yet, prolonged exposure to intense solar activity could weaken this protective barrier. The weakening of Earth's magnetic field would not only expose us to increased radiation, but also disrupt global navigation systems that rely on magnetic fields for orientation. Additionally, it could lead to more frequent geomagnetic storms, which have been known to interfere with satellite communications and power grids. As solar flares strip away Earth's atmosphere, the planet might become more similar to Mars, an arid landscape with no breathable air and extreme temperature variations. Life would struggle to survive in such harsh conditions, yet this scenario highlights how external forces can reshape planetary environments over time. The very elements that sustain life on Earth, carbon, nitrogen, oxygen, are forged in the cores of stars like our Sun before being scattered across space. In the distant future, as solar flares erode Earth's atmosphere, they also highlight the transient nature of habitability. Planetary systems evolve over billions of years, influenced by the aging and activity of their host stars. Our Sun is currently in its stable middle age, but will eventually expand into a red giant, engulfing Mercury and Venus before shrinking into a white dwarf. This evolutionary path underscores how cosmic events shape the fate of planets, leaving behind traces of once thriving ecosystems. Imagine standing at the edge of a desert that stretches for 10 kilometers in every direction where once lush forests thrived. The wind carries remnants of ancient pollen and leaves, evidence of an atmosphere that now barely clings to our planet. As solar flares continue their relentless assault on Earth's protective shield, regions previously teeming with life become barren wastelands. This transformation mirrors the cycles seen in other celestial bodies, planets like Mars that once held promise for sustaining life, but have since lost their atmospheres through similar processes. The slow erosion of our atmosphere serves as a reminder of how fragile planetary conditions can be. The cumulative effect of solar flares on Earth's atmosphere could lead to significant changes in atmospheric composition over time. The thinning of our protective layer would not only expose us to increased radiation, but also alter weather patterns and climate systems. This shift could dramatically affect agriculture, leading to food shortages and further challenges for survival. Yet, amidst this potential future, there is a paradox. While solar flares threaten life on Earth, they are also essential in the formation of elements that make life possible elsewhere in the universe. Despite these challenges, Earth's resilience is remarkable. Even with increased radiation and temperature extremes, some extremophiles, microorganisms adapted to harsh environments, might persist in niches such as deep-sea vents or polar ice caps. These hardy life forms demonstrate the tenacity of life itself, capable of adapting to changing conditions over eons. Yet, for complex multicellular organisms like humans, survival would require radical adaptations or relocation off-world. The possibility of human habitation on other celestial bodies becomes increasingly relevant as Earth's habitability wanes. The thinning atmosphere would not only affect surface conditions, but also impact the upper layers of Earth's crust through increased erosion rates. With less protection from cosmic radiation, chemical reactions in the soil could accelerate, altering nutrient cycles and ecosystem dynamics. This shift highlights how interconnected all aspects of The signals from the cosmic microwave background radiation are among the oldest and faintest whispers of our universe's origins. These photons have traveled for nearly 14 billion years, carrying information about conditions just 300,000 years after the Big Bang. They now fill the vastness of space with a temperature colder than any naturally occurring place on Earth. To capture these signals, scientists deploy highly sensitive instruments cooled to within millikelvin temperatures. These detectors are placed in orbit or deep within shielded chambers on Earth. The challenge lies not only in capturing such minute variations, but also filtering out interference from our own planet's thermal noise. This careful calibration ensures that the data collected is pure cosmic microwave background radiation, undistorted by terrestrial contamination. The process of analyzing these signals involves complex algorithms to separate the signal from noise. These algorithms sift through terabytes of data collected over years, revealing patterns in temperature fluctuations across different parts of the sky. Each variation tells a story about the distribution of matter and energy at the dawn of time, informing us about how galaxies and stars eventually formed. The cosmic microwave background also holds clues about future cosmological events. By studying these ancient signals, scientists can predict how galaxies will cluster together in billions of years and what fate awaits our universe, whether it will continue expanding indefinitely or eventually collapse under its own gravity. This knowledge places humanity in a unique position to understand not just our place within the cosmos, but also the ultimate destiny of all that exists. These signals are remnants from when the universe was dense enough for photons to interact with matter, creating a uniform glow across the sky. Today, this radiation is so faint that it can only be detected by highly specialized equipment. Yet, it provides crucial insights into the early universe's structure and composition, offering clues about how galaxies and stars eventually formed. The significance of these signals extends beyond mere scientific curiosity. They serve as tangible evidence linking every atom on Earth back to the primordial fireball from which everything emerged. In this sense, each of us is part of a much larger narrative, connected by the faint radiation left behind when the universe was born. This connection underscores our place in the cosmos and highlights the intricate balance that allows life to exist on Earth. The cosmic microwave background radiation we detect today has traveled across 13.8 billion years of expanding space. It originated from a time when the universe was only 379,000 years old, infantile by cosmic standards. At this age, the universe had cooled enough for protons and electrons to combine into neutral hydrogen atoms, allowing photons to travel freely without constant collisions. This event marked the end of the cosmic dark ages and the beginning of what astronomers call recombination. Each photon from the cosmic microwave background has been stretched by the expansion of space, shifting its wavelength from microwave to radio frequencies. The journey through time has left these particles with an average temperature of 2.725 Kelvin, just above absolute zero. This temperature is colder than any naturally occurring place on Earth, even Antarctica's coldest recorded temperatures. Yet, in a laboratory setting, scientists can artificially achieve temperatures far below this by using cryogenic coolants. The cosmic microwave background radiation fills every corner of the observable universe uniformly, but with tiny variations that map out the seeds from which galaxies and clusters formed. These fluctuations are so minute, about 1 part in 100,000, that detecting them requires instruments capable of measuring temperature differences down to a few millionths of a degree. Understanding these variations helps us trace back the initial conditions of our universe, revealing how quantum fluctuations during inflation could have sown the seeds for all cosmic structures. By studying the cosmic microwave background, scientists can also infer properties about dark matter and dark energy, which together make up over 95% of the mass energy content of the universe. These mysterious components influence the large-scale structure formation, but do not emit or absorb light directly, making them invisible to traditional telescopes. The cosmic microwave background provides a unique window into their effects on cosmic evolution. The precision with which we measure these ancient photons is remarkable. It's as if we are looking at a baby picture of our universe, capturing. The human brain is wired to recognize patterns and make predictions based on past experiences. This cognitive bias helps us navigate our environment efficiently, but it can also lead to overconfidence in familiar situations. For instance, when faced with a novel problem, we often rely too heavily on previous solutions that may not be applicable. Evolution has shaped human cognition to prioritize immediate threats and rewards, which is why we are more likely to focus on short-term gains rather than long-term benefits. This bias can manifest in various ways, such as preferring instant gratification over delayed satisfaction, or reacting strongly to imminent dangers while underestimating gradual risks like climate change. One surprising aspect of these biases is their persistence, even when they no longer serve survival purposes. For example, humans tend to fear flying despite it being statistically safer than driving. This irrational fear persists because our brains are better equipped to process vivid, immediate threats rather than abstract, long-term probabilities. Another cognitive bias worth noting is the confirmation bias, where individuals seek out information that aligns with their existing beliefs while ignoring contradictory evidence. This tendency can be particularly dangerous in decision-making processes, as it leads to a skewed perception of reality and hinders critical thinking. Interestingly, these biases are not unique to humans, but have evolved across various species as survival mechanisms. For instance, animals often exhibit risk-averse behaviors when faced with potential threats, even if those risks do not pose an immediate danger. This demonstrates how deeply ingrained such cognitive patterns can be in biological systems. Understanding and acknowledging these biases is crucial for developing more effective strategies to counteract their negative effects. By recognizing our tendencies toward overconfidence or confirmation bias, we can work towards making more informed decisions that better align with long-term goals and well-being. The human brain's capacity for pattern recognition extends beyond immediate survival to include social interactions as well. We are wired to detect subtle cues in body language and tone of voice, which helps us navigate complex social hierarchies. However, this skill can also lead to misinterpretations or overgeneralizations about others' intentions. For example, people often attribute negative motives to those who act differently from them without considering alternative explanations. This tendency, known as the fundamental attribution error, can foster misunderstandings and conflicts in both personal relationships and broader societal contexts. It underscores how deeply our cognitive biases influence not only individual behavior, but also collective dynamics. Moreover, these social cognitive biases have far-reaching implications for group decision-making processes. In collaborative settings, individuals may resist new ideas that challenge their preconceived notions, leading to stagnation or ineffective strategies. Recognizing this bias allows us to foster more inclusive environments where diverse perspectives are valued and integrated into problem-solving approaches. Understanding the origins of these cognitive biases provides valuable insights into human behavior across different contexts. By recognizing how evolution has shaped our brains to prioritize certain types of information over others, we can better appreciate why some patterns persist even when they no longer serve practical purposes. This awareness encourages a more nuanced approach to understanding both individual and collective behaviors. Evolutionary pressures have also influenced the development of heuristic shortcuts in human cognition. These mental rules of thumb allow us to make quick decisions without expending excessive cognitive resources. While these heuristics are generally efficient, they can sometimes lead to systematic errors known as cognitive biases. For instance, the availability heuristic causes individuals to overestimate the likelihood of events based on how easily examples come to mind. This bias often results in disproportionate attention being given to highly publicized incidents compared to less sensational but more frequent occurrences. In addition, loss aversion is another key heuristic that has evolved to protect resources vital for survival. People tend to feel losses much more intensely than equivalent gains, leading them to take greater risks too. In the heart of a star like our Sun, temperatures soar to 13 million degrees Celsius. This intense heat triggers nuclear fusion reactions, where hydrogen atoms fuse into helium. Each second, the Sun converts millions of tons of hydrogen into energy and heavier elements. Yet paradoxically, Stars are not eternal. They have finite lives determined by their mass and fuel supply. Deep within these stellar furnaces, elements heavier than iron are forged through a process called neutron capture. Neutrons bombard atomic nuclei, creating isotopes that eventually decay into stable elements. This process occurs in the final stages of massive stars, moments before they explode as supernovae. These explosions scatter the newly formed elements across space, seeding future generations of stars and planets. Consider Earth's iron core, a remnant from ancient stellar deaths. The iron in your blood was once part of a star that died long before our sun existed. This cosmic recycling process has been ongoing for billions of years, shaping the chemical composition of galaxies. Each atom in your body is a testament to this relentless cycle of creation and destruction. The process by which stars produce elements heavier than hydrogen is not instantaneous, but occurs over eons. Stars like Betelgeuse, visible in our night sky, are currently fusing helium into carbon and oxygen. When it eventually goes supernova, it will scatter these elements across the cosmos. This event will take place in mere seconds, yet its preparation has spanned millions of years. These heavy elements play a crucial role in Earth's formation and evolution. They contribute to the planet's magnetic field, which protects us from harmful cosmic radiation. The iron core generates this protective shield through convection currents that create electric charges as they move through Earth's outer core. This process ensures a stable environment conducive to complex life. The universe is constantly renewing itself through specific stellar processes. Stars are born, live, and die, each contributing to the elemental diversity of the cosmos. For instance, when a star like Betelgeuse goes supernova, it will release enough energy in a few seconds to outshine entire galaxies for weeks. This explosive event scatters elements across space at speeds up to 10% the speed of light, seeding future generations of stars and planets. In the heart of a star like our Sun, temperatures soar to 13 million degrees Celsius. This intense heat triggers nuclear fusion reactions, where hydrogen atoms fuse into helium. Each second, the Sun converts millions of tons of hydrogen into energy and heavier elements. Yet paradoxically, stars are not eternal. They have finite lives determined by their mass and fuel supply. Deep within these stellar furnaces, elements heavier than iron are forged through a process called neutron capture. Neutrons bombard atomic nuclei, creating isotopes that eventually decay into stable elements. This process occurs in the final stages of massive stars, moments before they explode as supernovae. These explosions scatter the newly formed elements across space, seeding future generations of stars and planets. Consider Earth's iron core, a remnant from ancient stellar deaths. The iron in your blood was once part of a star that died long before our sun existed. This cosmic recycling process has been ongoing for billions of years, shaping the chemical composition of galaxies. Each atom in your body is a testament to this relentless cycle of creation and destruction. The process by which stars produce elements heavier than hydrogen is not instantaneous, but occurs over eons. Stars like Betelgeuse, visible in our night sky, are currently fusing helium into carbon and oxygen. When it eventually goes supernova, it will scatter these elements across the cosmos. This event will take place in mere seconds, yet its preparation has spanned millions of years. These heavy elements play a crucial role in Earth's formation and evolution. They contribute to the planet's magnetic field, which protects us from harmful cosmic radiation. The elements that make up our planet were once scattered in space before coalescing into planets like Earth. This cycle underscores the interconnectedness of all celestial bodies and their role in shaping life as we know it. In the heart of a star like our Sun, temperatures soar to 13 million degrees Celsius. This intense heat triggers nuclear fusion reactions, where hydrogen atoms fuse into helium. Each second, the Sun converts millions of tons of hydrogen into energy and heavier elements. Yet paradoxically, stars are not eternal. They have finite lives determined by their mass and fuel supply. As you begin your ascent from Earth's surface, the first noticeable change is a decrease in air pressure and temperature. At sea level, the atmospheric pressure is approximately 10-13 millibars, while the average temperature hovers around 15 degrees Celsius. As you climb higher, these values drop steadily. By reaching an altitude of just 3 kilometers, you have already left behind most commercial aircraft flights, where the air pressure is roughly half that at sea level. The sensation of thinning air becomes more pronounced as you continue your journey upward. At 10 kilometers above Earth's surface, the temperature can dip to -56 degrees Celsius, colder than many Arctic regions. This layer, known as the tropopause, marks the boundary between the turbulent lower atmosphere and the calmer stratosphere. Here, the sky appears a deeper shade of blue due to less scattering of sunlight by air molecules. The thinning air also means that sound waves struggle to propagate, making this region eerily silent compared to Earth's surface. Ascending further into the stratosphere, you encounter an unexpected phenomenon. Despite the increasing altitude and thinner atmosphere, temperatures begin to rise again. By reaching 20 kilometers in altitude, temperatures can climb back up to -50 degrees Celsius. This warming trend is due to the presence of ozone, which absorbs ultraviolet radiation from the sun and converts it into heat. However, this same layer also contributes to a paradoxical effect. While protecting life on Earth by shielding us from harmful ultraviolet rays, the ozone layer also traps some infrared radiation, exacerbating the greenhouse effect. At 50 kilometers above Earth, you enter the mesosphere, where temperatures plummet once more, reaching as low as -90 degrees Celsius. This region is home to an average of about 10 meteors per square kilometer that burn up in the upper atmosphere each day. These meteor showers provide valuable insights into the composition of our solar system's early days. The tiny particles are remnants from the formation of planets and stars, forged in distant stellar furnaces billions of years ago. Continuing your ascent beyond 100 kilometers, you leave behind Earth's thermosphere and enter the exosphere, where air molecules become increasingly sparse. Here, pressure drops to less than a billionth of an atmosphere, making it impossible for a human to survive without specialized equipment. The temperature can reach as high as 1,300 degrees Celsius due to the absorption of solar radiation by oxygen atoms. This paradoxical heat occurs because there are few molecules available to distribute this energy evenly, leading to localized spikes in temperature. As you approach the boundary where Earth's atmosphere meets the vacuum of space, you notice a significant drop in pressure and temperature once more. At an altitude of about 400 kilometers, the International Space Station orbits Earth, experiencing microgravity conditions that allow objects to float freely. The station's crew must rely on artificial environments to survive, as the thin air at this height provides insufficient oxygen for human respiration. This fragile boundary is a stark reminder of how delicate our atmosphere truly is and how essential it is for life on Earth. From a spacecraft orbiting Earth, you might observe the night side of our planet glowing softly under the influence of airglow, a phenomenon where chemical reactions in the upper atmosphere are illuminated by cosmic rays and solar radiation. This light bends slightly as it passes through the atmosphere, creating a subtle glow around city lights. In contrast, distant galaxies emit their own light without such atmospheric interference. The energy from these far-off stars reaches us in discrete packets known as photons, each carrying information about its source. These photons travel for billions of years before they reach our telescopes, offering insights into the life cycles and eventual fates of stars that have long since ceased to exist. Consider the luminosity of a typical human city at night. Its lights are powered by electricity generated from various sources like coal, natural gas, or renewable energy. The total output for an average-sized city might be around 1 gigawatt, enough to light up several neighborhoods. In comparison, the nearest galaxy, Andromeda, is estimated to produce a luminosity equivalent to 3 trillion suns. The scale of this difference is staggering when you consider that each star in Andromeda has been burning for billions of years, while city lights are fleeting by comparison. The energy from these distant stars has traveled across 2.5 million light-years before they reach Earth, yet the light from our cities fades with just a few miles of distance. This contrast highlights not only the longevity of stellar life, but also the brief and concentrated nature of human civilization's artificial lighting. Imagine standing in an observatory on Earth, peering through a telescope at distant galaxies. The faint glow you see is the accumulated light from billions upon billions of stars, each one contributing to the overall luminosity. This collective brightness allows astronomers to measure distances across the universe and understand how galaxies have evolved over time. In this way, the faint glow of far-off galaxies serves as a cosmic map, helping us chart the vastness of space. While city lights may seem bright at night, they are insignificant when compared to the luminosity of distant galaxies. The energy output from our cities is concentrated in a small area and fades quickly with distance, whereas the light from galaxies travels across billions of light-years before reaching Earth. This disparity underscores both the transient nature of human activities and the enduring presence of cosmic phenomena that have shaped the universe for eons. The energy consumed by a typical city at night, such as Tokyo or New York, could power millions of homes, but pales in comparison to the output of even a single star within a distant galaxy. For instance, the Sun alone emits more than 386 yottawatts, equivalent to 1 trillion times the total energy consumption of Earth. This disparity is further magnified when considering entire galaxies like Andromeda or the Sombrero Galaxy, whose combined light output far surpasses anything human civilization can generate. The sheer magnitude of this difference not only highlights the immense power of stars, but also underscores our planet's relatively minor role in the cosmos. The lifespan of city lights versus stellar luminosity presents an interesting contrast as well. City lights flicker on and off within hours, while stars burn for billions of years, their energy output a testament to the longevity of nuclear fusion processes deep within their cores. This enduring light from distant stars allows astronomers to study the history of galaxies, tracing back through cosmic time to understand how these massive structures have evolved over eons. In this way, the faint glow of far-off galaxies serves as a window into the past, offering insights into the universe's earliest moments and the processes that shaped its current form. Within our own solar system, Earth is unique in its ability to support liquid water and complex life forms due to its position within the habitable zone. However, this delicate balance contrasts sharply with the harsh conditions found elsewhere in the cosmos. The extreme temperatures and radiation levels encountered beyond our planet's protective atmosphere make it impossible for human life to exist without technological intervention. Yet, despite these challenges, the energy output of distant stars continues to illuminate vast stretches of space, offering a glimpse into the grandeur of the universe on scales far removed from our everyday experience. For instance, while Earth is teeming with life, some exoplanets in other star systems are known to have conditions that could potentially support forms of life vastly different from what we know, suggesting that our understanding of habitability might be limited by our own experiences. The sun will continue to shine. The very act of mountain formation exemplifies how localized systems can build structure against the backdrop of a universe drifting toward uniformity. Tectonic plates grind together, creating peaks and valleys that defy the cosmic trend toward disorder. This process occurs at an imperceptible pace, mere centimeters annually, but over millennia, it shapes landscapes that are both familiar and awe-inspiring. Water cycles throughout Earth's ecosystems serve as another vivid example of ordered processes at work. A single water molecule may journey from deep underground to high clouds and back again, driven by forces that maintain balance rather than dissolve into randomness. Each phase transition, from vapor to liquid to ice, requires energy input, a temporary resistance against the natural diffusion of heat. This cycle exemplifies how life harnesses available energy to perpetuate order. In contrast to Earth's ordered systems, consider deep space, where entropy reigns supreme. The vast expanses between stars are nearly empty, filled with particles that drift freely without interacting. In such environments, there is no mechanism for generating or maintaining localized complexity. This stark difference underscores how unique and precious life-supporting systems on Earth truly are, small but significant islands of order in a universe increasingly governed by entropy. Earth's magnetic field provides another layer of resistance against cosmic disorder. Generated by the churning liquid iron in our planet's core, this shield deflects harmful solar winds and cosmic radiation, protecting the delicate ecosystems that have evolved here. The strength of Earth's magnetic field at the surface ranges from 25 to 65 microteslas, a force that may seem weak but is crucial for life as we know it. The atmosphere itself plays a vital role in maintaining order on our planet. It contains about 78% nitrogen and 21% oxygen, with trace amounts of other gases like argon and carbon dioxide. This mixture not only supports respiration, but also regulates temperature through the greenhouse effect. Without this protective blanket, Earth would be an inhospitable place, subject to extreme temperature fluctuations and constant bombardment by cosmic particles. Plants contribute significantly to the battle against entropy on Earth. Through photosynthesis, they convert sunlight into chemical energy, producing oxygen as a byproduct. This process not only sustains life, but also helps regulate the planet's climate by absorbing carbon dioxide. The intricate balance of this system is finely tuned, with each organism playing its part in maintaining the delicate equilibrium that supports all life on our planet. Consider the Earth's water cycle, a constant process of transformation and renewal. Water evaporates from oceans, lakes, and rivers, rises into the atmosphere, condenses into clouds, and eventually returns to the ground as rain or snow. This cycle operates on timescales ranging from minutes for cloud formation to millennia for deep groundwater reservoirs. Each drop of water in this cycle participates in a dance that defies the second law of thermodynamics, maintaining order through continuous circulation. The energy required to drive this cycle comes primarily from solar radiation, which powers evaporation and drives atmospheric convection. Without this relentless recycling, Earth would become a static, lifeless sphere. The paradox deepens when we consider plate tectonics, the slow but powerful engine that shapes our planet's surface. Tectonic plates move at an imperceptible rate of about 4 centimeters per year, driven by heat from the Earth's core. This process not only creates mountains and ocean basins, but also recycles rocks back into the mantle, where they are melted and reformed. Plate tectonics is a complex interplay of forces that resists entropy on geological timescales. It ensures that new crust forms at mid-ocean ridges, while old crust subducts beneath continents, creating dynamic landscapes. This constant reshaping of Earth's surface contrasts with the universe's tendency toward uniformity and simplicity. Life itself plays a crucial role in maintaining order against cosmic disorder. Organisms consume energy to grow, reproduce, and maintain their structures, thereby resisting entropy at biological scales. Photosynthesis by plants converts sunlight into chemical energy stored as glucose, fueling ecosystems worldwide. This process not only sustains life, but also regulates Earth's atmosphere through the exchange of gases like oxygen and carbon dioxide. The biosphere is a self-regulating system that thrives within narrow environmental limits, limits set precisely by the conditions necessary for life to flourish. Human technology further exemplifies this struggle against The interaction between plate tectonics and ocean currents is a complex dance that shapes Earth's climate over millions of years. Tectonic plates move at an average rate of 4 centimeters per year, shifting continents and creating new coastlines. This slow movement influences the formation of ocean basins, which in turn affects global circulation patterns. For instance, the Gulf Stream carries warm water from the tropics toward higher latitudes, playing a crucial role in regulating temperatures across North America and Europe. Ocean currents are not just passive recipients of tectonic influence, they also shape the landscape beneath them. As deep ocean waters rise to the surface through upwelling zones near coastlines, nutrient-rich water supports marine ecosystems. This process is vital for fisheries and other industries that depend on healthy oceans. The nutrients carried by these currents can be traced back to volcanic activity at mid-ocean ridges, where magma rises from Earth's mantle to form new crust. These underwater mountains are the birthplace of many oceanic features. The relationship between tectonics and climate is further complicated by feedback loops that amplify or dampen changes over time. For example, when continents drift apart, creating wider oceans, heat exchange between the poles and equator increases. This can lead to more stable climates globally. Conversely, when land masses converge, reducing oceanic circulation, temperature extremes become more pronounced. These dynamics have played out throughout Earth's history, contributing to periods of glaciation and warming. One surprising aspect of this interaction is how it affects weather patterns far from the immediate vicinity of tectonic activity. The movement of plates can influence atmospheric pressure systems thousands of kilometers away. For instance, the formation of mountain ranges like the Himalayas not only alters local climates, but also impacts global wind patterns and precipitation distribution. This demonstrates how changes at one location can have widespread effects on Earth's climate system. The long-term impact of tectonic activity on ocean currents is particularly evident when considering the deep past. About 250 million years ago, all continents were joined in a supercontinent called Pangaea. As this landmass began to break apart, it set off a chain reaction that reconfigured global climates and ecosystems. The resulting changes in ocean circulation patterns led to significant shifts in temperature and humidity across different regions of the planet. Today, scientists use complex models to predict how ongoing tectonic movements will influence future climate trends. By studying past geological events, they can better understand current processes and anticipate potential outcomes. This knowledge is crucial for addressing challenges such as rising sea levels and extreme weather conditions, which are increasingly affecting human societies around the world. The movement of tectonic plates also influences ocean currents through the formation of deep-sea trenches and ridges. These underwater features act as barriers or conduits for water flow, guiding vast bodies of seawater across the globe. For instance, the Mid-Atlantic Ridge, a major undersea mountain chain, helps drive the thermohaline circulation, a global conveyor belt that redistributes heat from tropical regions towards polar areas. This process plays a critical role in regulating Earth's climate by moderating temperature extremes and supporting diverse marine ecosystems. In contrast to the slow but steady movement of tectonic plates, ocean currents can change more rapidly due to fluctuations in wind patterns or variations in sea surface temperatures. However, over geological timescales, these dynamic interactions between land masses and oceans shape long-term climatic trends. The interaction is so profound that researchers sometimes refer to Earth as a geophysical fluid dynamics machine, where the solid Earth and liquid oceans work together to maintain balance on this spinning blue planet. At a depth of 4 kilometers beneath the ocean's surface, near hydrothermal vents, the water boils at temperatures exceeding 350 degrees Celsius. This superheated fluid contrasts sharply with the surrounding seawater, which hovers around 1 degree above freezing. The pressure here is immense, reaching over 200 atmospheres, yet life thrives in this extreme environment. These creatures have adapted to conditions that would be lethal for most other organisms on Earth, showcasing nature's capacity for resilience and adaptation. Surrounding the vents are tube worms, some growing up to 3 meters long, anchored by roots that absorb chemicals from the vent fluids. They house symbiotic bacteria within their bodies, which convert these chemicals into energy through chemosynthesis. This process is akin to photosynthesis on land, but uses chemical energy instead of sunlight. The worm's survival underscores how life can flourish in environments devoid of light and oxygen, offering insights into potential life forms elsewhere in the universe. At this depth, sound travels differently than it does at the surface. The water here acts as a conduit for low-frequency sounds, allowing them to propagate over vast distances. These infrasound waves carry information about seismic events and other disturbances, creating an auditory map of the deep ocean's activity. This acoustic environment is crucial for communication among vent-dwelling organisms, but imperceptible to human ears without specialized equipment. For instance, certain species of shrimp use high-frequency clicks to navigate in the dark, while tube worms detect vibrations through their bodies to sense potential threats or mates. The complexity of these soundscapes reflects specific adaptations and interactions unique to this ecosystem. Hydrothermal vents are often found along tectonic plate boundaries, where seawater seeps into cracks and is heated by magma. This process creates a unique ecosystem teeming with extremophiles, organisms adapted to extreme conditions. These creatures thrive on chemical energy rather than sunlight, challenging our understanding of life's limits. Some vent organisms host symbiotic bacteria that convert toxic chemicals like hydrogen sulfide into organic compounds, providing sustenance in an otherwise barren environment. This self-sustaining system highlights the resilience and adaptability of life, suggesting that similar ecosystems could exist elsewhere in the universe. Despite the harsh conditions at hydrothermal vents, they are home to a diverse array of species, including tube worms, crabs, and shrimp. These animals have evolved specialized organs to withstand the extreme temperatures and chemicals present. For example, some shrimp possess heat-resistant enzymes that allow them to thrive near boiling water. The tube worms lack digestive systems and instead rely on bacteria living within their tissues to provide nutrients. This symbiotic relationship underscores the interconnectedness of life forms in even the harshest environments. While these creatures are adapted to thrive at hydrothermal vents, they would struggle to survive elsewhere, illustrating how finely tuned evolution can be. The sound near a deep ocean hydrothermal vent is not what one might expect. Instead of silence, there's a constant hum from the movement of water and the activity of organisms. This noise, though faint, carries information about the environment's dynamics. The pressure waves created by these sounds travel through water, but would be inaudible to human ears without amplification. In contrast, on land, sound travels through air, which is less dense than water, affecting how we perceive it. Near a vent, the boiling water and strange creatures create an auditory landscape that is both alien and alive. The temperature near hydrothermal vents can reach over 350 degrees Celsius, while just a few meters away, the surrounding seawater remains close to freezing. This dramatic contrast in temperatures creates convection currents that drive nutrient-rich waters upward, feeding the unique ecosystem around the vent. These conditions are similar to those found on early Earth, where volcanic activity provided heat and chemicals necessary for life's origins. The creatures here have adapted to this extreme environment, thriving in a place most organisms would find inhospitable. Their survival strategies offer insights into how life might exist elsewhere in the universe. Hydrothermal vents are home to chemosynthetic bacteria that convert sulfur compounds into energy, forming the base of these ecosystems. These microbes do not rely on sunlight for photosynthesis, but instead harness chemical energy from their surroundings. This process is akin to what might have occurred billions of years ago when Earth was devoid of oxygen and life, as we know it had yet to evolve. The bacteria here are part of a web of interactions that sustain the vent's ecosystem, with larger organisms like tube worms and shrimp feeding on them or each other. Each organism plays a crucial role in maintaining this delicate balance. Surrounding the vents, you would see towering chimneys made of minerals deposited by the superheated water as it cools and interacts with colder seawater. These structures can grow to heights of up to 30 meters, creating an alien landscape teeming with life. The temperature difference between the vent fluids and the surrounding ocean is stark, reaching over 300 degrees Celsius at the source, while the ambient sea temperature remains just above freezing. This gradient drives the chemical reactions that sustain these ecosystems, a process that mirrors the heat-driven convection currents in Earth's mantle. Imagine standing near one of these vents, where boiling water and strange creatures coexist. The sound would be more muted than you might expect, given the turmoil around you. Hydrothermal vent communities are isolated from the surface world, yet they thrive under conditions that seem inhospitable to most life forms. These ecosystems have adapted to extreme pressures, temperatures, and chemical environments, showcasing nature's resilience in the face of adversity. The moon's gravitational influence on Earth extends beyond just tides. It subtly affects biological rhythms as well. For instance, studies suggest that menstrual cycles in women may synchronize with lunar phases, a phenomenon known as the lunar hypothesis. This connection between celestial mechanics and human biology is both intriguing and complex. Consider the moon's surface temperature, which can drop to -173 degrees Celsius during its long night. In contrast, Earth maintains an average surface temperature of about 15 degrees Celsius due to its atmosphere and oceans. These temperatures are crucial for sustaining life on our planet, but starkly highlight how different environments can be in just a small step from one celestial body to another. The moon's gravitational pull causes the Earth to wobble slightly on its axis, which is responsible for the slight variation in the length of each day, known as lunar precession. This effect adds or subtracts up to 2 milliseconds per century. While this might seem insignificant, it underscores how small forces can have long-term impacts on our planet's rotation. Interestingly, the moon's influence on Earth extends even deeper than just surface phenomena. The gravitational pull affects the distribution of mass within the Earth itself, leading to changes in the shape of continents and oceans over time. This tidal interaction is so powerful that it has been proposed as a potential mechanism for synchronizing biological rhythms, including menstrual cycles with lunar phases. The moon's orbit around Earth is not perfectly circular, but elliptical, causing variations in its distance from our planet by about 42,000 kilometers over the course of each month. This fluctuation impacts tidal forces and can lead to more extreme high tides during certain times of the year. These changes are subtle yet significant, influencing coastal ecosystems and even human activities like fishing. Interestingly, while we often think of the moon as a static companion in the sky, it is gradually moving away from Earth at a rate of about 3.8 centimeters per year. This slow drift is due to tidal friction caused by the gravitational interaction between the two bodies. Over billions of years, this process will eventually lead to longer days and less pronounced tides on our planet. Yet, for now, the moon continues its steady orbit, maintaining a rhythm that influences not just the oceans, but also biological cycles deep within living organisms. The gravitational pull of the moon is responsible for creating 2 high tides each day as Earth rotates beneath it. This phenomenon is known as lunar diurnal inequality, where the tidal range varies slightly from one high tide to the next. The moon's influence extends beyond just water. Some researchers suggest that its gravitational forces may also play a role in regulating menstrual cycles and other biological rhythms in humans. This connection between celestial mechanics and human biology underscores how deeply we are intertwined with our cosmic environment. Imagine standing on a beach as the tide recedes, revealing vast stretches of wet sand. The water level fluctuates by an average of 2 meters twice daily due to the moon's gravitational pull. However, this rhythmic ebb and flow is not uniform across all coastlines. Some areas experience much more dramatic tidal changes than others. In certain parts of Canada's Bay of Fundy, for instance, the tide can rise and fall by as much as 17 meters in a single day. This extreme variation highlights how local geography interacts with global gravitational forces to create unique environmental conditions. The moon's influence extends beyond just tides. It also subtly affects biological rhythms on Earth. For example, many marine organisms time their reproductive cycles with the lunar phases. Some species of fish and crustaceans release eggs or larvae during specific tidal events, ensuring that offspring are carried into nutrient-rich waters by currents. Interestingly, this connection between celestial bodies and life's internal clocks is not limited to marine environments. Studies suggest that human menstrual cycles may also exhibit a slight correlation with the lunar phases, though this relationship remains less well understood and more controversial in scientific circles. The gravitational pull of the moon causes Earth's oceans to bulge outward on both sides of the planet, creating two high tides each day. This tidal force is so powerful that it gradually slows down Earth's rotation by about 1.7 milliseconds per century. Over millions of years, this effect has lengthened our days and pushed the moon farther away from Earth at a rate of approximately 38 millimeters each year. In contrast, the moon's own rotational period matches its orbital period around Earth, meaning it always shows the same face to us, a phenomenon known as tidal locking. This synchronous rotation is not unique. Many moons in the solar system exhibit similar behavior. The connection between lunar cycles and biological rhythms on Earth extends beyond just tides. Some researchers suggest that the moon's gravitational influence may also affect other cyclical processes, such as menstrual cycles in humans. While this link remains speculative, it underscores how deeply interconnected our planet is with its natural satellite. The moon's orbit around Earth takes 27 days to complete one full cycle relative to distant stars, a period known as sidereal month, while the synodic month, measured from new moon to new moon, lasts about 29.5 days. This subtle variation in orbital periods contributes to the complex interplay between lunar phases and terrestrial phenomena. The moon's gravitational pull on Earth not only stabilizes our planet's axial tilt, but also influences oceanic tides through. The Earth's biosphere and geological processes have co-evolved over billions of years, creating intricate feedback loops that maintain balance in our ecosystem. Consider the carbon cycle, where plants absorb carbon dioxide through photosynthesis. Animals consume these plants, and when organisms die, their remains decompose, returning carbon to the soil or oceans. This cycle stabilizes atmospheric CO2 levels, crucial for regulating Earth's temperature. Yet this delicate balance is not static. It has evolved alongside geological processes like volcanic activity, which releases gases that can alter climate patterns over millennia. The interplay between living organisms and rock formations ensures a dynamic equilibrium, constantly adjusting to changes in the environment. Imagine standing at the edge of a forest where roots intertwine with ancient bedrock. These roots extract nutrients from rocks broken down by weathering, a process known as chemical weathering. This interaction not only sustains life, but also shapes the landscape over time. The iron and calcium extracted from rocks are essential for plant growth, while the carbon dioxide absorbed in this process helps regulate Earth's atmosphere. Remarkably, this cycle has been ongoing for billions of years, long before humans walked the Earth. It is a testament to how geological processes have co-evolved with life, creating feedback loops that maintain balance in our ecosystem. Consider the role of volcanic activity in maintaining atmospheric composition. Volcanoes release gases such as carbon dioxide and sulfur dioxide into the atmosphere. Over millions of years, these emissions play a crucial part in regulating Earth's temperature. The sulfur aerosols from volcanoes can cool the planet by reflecting sunlight back into space, while carbon dioxide contributes to the greenhouse effect. This delicate balance has allowed life to flourish on our planet for billions of years. Yet, paradoxically, the very same volcanic activity that sustains us also poses a threat. Large-scale eruptions have caused mass extinctions in Earth's history, such as the one that wiped out the dinosaurs 66 million years ago. These events remind us how finely tuned our biosphere is and how easily it can be disrupted. The surface of Earth is not static. It constantly shifts due to plate tectonics. This process involves the movement of massive slabs of rock, each weighing trillions of tons. The heat from Earth's core drives this motion, creating a dynamic interplay between geological and biological systems. For instance, volcanic activity releases gases like carbon dioxide into the atmosphere, which plants then absorb to grow. In turn, these plants contribute organic matter that eventually becomes sedimentary rocks. This cycle underscores how life on Earth has co-evolved with its rocky substrate over billions of years. Remarkably, this process also influences climate patterns, as variations in volcanic emissions can alter global temperatures by changing the concentration of greenhouse gases in the atmosphere. Consider the role of ocean currents in this intricate dance between biology and geology. These vast rivers of water are driven not only by wind, but also by the movement of tectonic plates beneath the sea floor. As continents shift, they create new coastlines and alter the flow of these currents. For instance, the formation of the Isthmus of Panama some 3 million years ago separated the Atlantic and Pacific Oceans, leading to a significant change in ocean circulation patterns that cooled the planet. This cooling event not only influenced global climate, but also altered marine ecosystems by creating new habitats for species to evolve. The interplay between geological processes and biological adaptation is a delicate balance where small changes can have profound effects on life across the globe. Imagine standing at the edge of a deep-sea hydrothermal vent where superheated water bursts forth from cracks in the Earth's crust. These vents are hotspots for chemical reactions that sustain unique ecosystems far removed from photosynthesis. The temperature difference between the vent fluids and surrounding seawater can be as extreme as 300 degrees Celsius. This thermal gradient drives a constant flow of minerals and nutrients, creating conditions ideal for chemosynthetic bacteria at the base of these food chains. These bacteria do not rely on sunlight, but instead harness energy from chemical reactions involving hydrogen sulfide, a compound abundant in vent fluids. The paradox here is that life thrives in environments devoid of light, challenging our assumptions about what constitutes a livable habitat. Consider how Earth's magnetic field acts like a protective shield against cosmic radiation and solar winds. With strengths ranging from 25 to 65 microteslas at the surface, this invisible force deflects harmful particles away from life on the planet. The core of our planet, composed largely of iron and nickel, generates this field through convection currents. These currents are driven by heat escaping from Earth's core, which is hotter than the surface of the Sun, reaching temperatures exceeding 13 million degrees Celsius. This heat not only powers the magnetic field, but also fuels plate tectonics, shaping continents over millions of years. The interplay between these geological processes and life forms a delicate feedback loop that has sustained Earth's habitability for billions of years. Life on Earth has adapted to this dynamic environment, with organisms influencing atmospheric composition and soil chemistry in ways that further stabilize the planet's conditions. Consider the role of carbon dioxide in Earth's atmosphere. This gas, essential for photosynthesis, is also a potent greenhouse gas. Over geological timescales, plants and microorganisms have drawn down vast amounts of CO2 from the air, storing it as organic matter or carbonate rocks. Imagine stepping onto a neutron star, an object so dense that its surface gravity is unimaginably stronger than Earth's. At just 10 kilometers in diameter, this celestial body contains more mass than our Sun. The gravitational pull at its surface reaches 13.8 billion times that of Earth's. Under such conditions, your body would instantly be crushed into a state known as neutronium, where atomic nuclei are packed so tightly they form an unbreakable lattice. This extreme compression is not just a force of nature, it's a demonstration of the universe's relentless drive towards simplicity and density. The energy required to maintain this state far exceeds anything we can imagine on Earth. Neutron stars, despite their small size, typically only 10 kilometers in diameter, are among the densest objects known in the universe. They pack more mass than our Sun into a volume smaller than many cities. This extreme density is due to the collapse of massive stars, where protons and electrons merge under intense pressure, forming neutrons. The gravity at their surface reaches unimaginable levels, about 200 billion times Earth's gravitational pull. Imagine standing on such a neutron star. Your body would be crushed instantly, compressed into a state closer to that of atomic nuclei than recognizable flesh. In this environment, the atoms in your bones and tissues would rearrange themselves under extreme pressure, transforming you into something unrecognizable, matter so dense it defies imagination. The smallest neutron stars can pack more mass than our Sun within a sphere no larger than a city. Yet, despite their tiny size, they exert gravitational forces that dwarf even the most powerful black holes. Imagine standing on the surface of such an object. At 13.8 billion times Earth's gravity, your body would be compressed into a state where atoms are packed so tightly they form neutronium, a dense matter where atomic nuclei are locked in an unbreakable lattice. Every atom in your body would be crushed beyond recognition, rearranging themselves to fit the extreme pressure, transforming you into something far denser than any material known on our planet. Yet, despite this unimaginable force, neutron stars are only about 10 kilometers across, smaller than many cities. Neutron star gravity is so intense that it warps time itself according to Einstein's theory of relativity. Time near the surface moves slower compared to distant observers like us. This effect, known as gravitational time dilation, would cause a clock on the neutron star's surface to tick at a rate significantly different from one here on Earth. Yet, for any human unfortunate enough to approach such an object, the experience would be far too brief to notice. Imagine standing just outside the event horizon of a neutron star, where gravity pulls with a force equivalent to billions of times that of Earth's surface gravity. The crushing pressure would instantly compress your body into something akin to subatomic particles, defying any biological function. Despite its small size, typically only 20 kilometers in diameter, a neutron star can contain more mass than our Sun packed into this tiny sphere. This density is so extreme that it challenges the very definition of matter itself. Imagine a scenario where humans could somehow survive the initial approach to such an object, perhaps through advanced technology or unforeseen biological adaptations. Even then, the sheer force would tear apart any spacecraft and crush human bodies instantly upon contact with the neutron star's surface. The gravity at this point is approximately 100 billion times stronger than Earth's, meaning that a person standing on it would experience pressures equivalent to being compressed into an atom-sized speck. This extreme compression occurs because neutrons in such stars occupy less space than protons or electrons due to quantum effects. Despite the mind-boggling density of neutron stars, packing more mass than our Sun into a sphere roughly 10 kilometers wide, their surfaces are not solid ground where one could stand. Instead, they consist of an ultra-thin crust made mostly of iron-56 nuclei floating in a sea of degenerate neutrons. For comparison, if you were to compress all the water on Earth into neutron star material, it would fit inside a cube just 10 meters on each side. This density defies human intuition, as we are accustomed to objects expanding rather than contracting under pressure. Yet, this is the reality of extreme gravity environments. Neutron stars also emit powerful magnetic fields, up to 1 trillion times stronger than Earth's, which can influence the behavior of particles in their vicinity. Imagine being exposed to the intense gravitational pull of a neutron star, an object no larger than a city, but containing more mass than our Sun. The surface gravity would crush any human form instantly, pressing every atom together with such force that even light could not escape. This phenomenon, known as the event horizon, is where the escape velocity exceeds the speed of light. Yet, paradoxically, neutron stars are remnants of supernovae, explosions so powerful they can outshine entire galaxies for weeks. Imagine a human body exposed to such extreme gravitational forces. The internal organs would be crushed into an unimaginably dense state, far exceeding the density of any material on Earth. A single teaspoon of neutron star matter weighs as much as Mount Everest. This crushing force would compress atoms themselves, eliminating empty space between particles and creating conditions where nuclear physics reigns supreme. Despite its minuscule size, typically just 10 to 20 kilometers in diameter, a neutron star exerts gravitational forces that are inconceivable by earthly standards. If a mountain on Earth were scaled up to the size of Jupiter, it would still be less massive than this stellar remnant. The gravity at its surface is so intense that it compresses. Imagine standing on a barren landscape of early Earth, its surface pockmarked by impact craters from frequent collisions with comets and asteroids. These celestial bodies were not merely destructive forces. They carried within them vital ingredients for life, water, and organic compounds. Each impact delivered an average of 30 to 50,000 tons of water into the primordial oceans. Consider this. While Earth's surface temperature averages around 15 degrees Celsius, supporting liquid water essential for life, it was once a far more volatile place. 4 billion years ago, during what scientists call the Hadean Eon, our planet endured relentless bombardment by comets and asteroids. These celestial visitors delivered not just raw materials, but also the very building blocks of life. Each impact released an immense amount of energy, equivalent to 10,000 megatons of TNT, vaporizing rock and ejecting material into space. But amidst this chaos, water molecules found their way to Earth's surface, carried on the backs of comets. Each comet, a wandering ice ball from the outer reaches of our solar system, delivered precious cargo, water, and organic compounds essential for life as we know it. These icy messengers traveled through the void, some originating in the distant Oort cloud or the Kuiper belt, before colliding with Earth over billions of years. Each comet carried water and complex organic molecules crucial for life's origins. The average mass of a typical comet is around 1 billion metric tons, smaller than many mountains, but capable of delivering vast amounts of material to our planet. These icy messengers from the outer solar system, known as comets, played a crucial role in Earth's early history by delivering water and organic compounds necessary for life. Imagine an asteroid hurtling through the cosmos at 13 kilometers per second, destined to collide with Earth 4 billion years ago. This impact delivered more than just mass. It carried water and complex organic molecules essential for life. The surface temperature of early Earth was far hotter, reaching up to 200 degrees Celsius in some regions. Yet, it was during this tumultuous period that icy comets began their relentless bombardment. These celestial bodies, often traveling at speeds exceeding 50 kilometers per second, delivered not just water, but also organic compounds essential for life. Each comet collision would have scattered the building blocks of amino acids and nucleotides across Earth's surface. The average impact speed was around 20 kilometers per second, releasing energy equivalent to millions of atomic bombs. This relentless bombardment lasted for hundreds of millions of years, shaping the young Earth into a crucible of life. Each comet or asteroid collision delivered water and organic compounds essential for life. These icy bodies, some as large as cities, carried frozen water and complex molecules across the solar system. Each impact was a delivery service from the cosmos, bringing vital ingredients to a planet still in its infancy. The bombardment lasted for hundreds of millions of years, shaping Earth's surface and atmosphere. Each comet or asteroid collision delivered precious cargo, water and organic compounds essential for life. These icy bodies were like cosmic couriers, carrying molecules that would eventually form the building blocks of proteins and DNA. Each impact brought not just raw materials, but also a chaotic dance of energy and matter. The average surface temperature on Earth today is 15 degrees Celsius, which supports liquid water, a critical ingredient for life as we know it. Yet billions of years ago, when our planet was young, the surface was molten and inhospitable. During this period, known as the Late Heavy Bombardment, Earth received a constant barrage of comets and asteroids. These celestial bodies delivered more than just impact craters. They carried water and organic compounds essential for life. Each comet that struck Earth contained ice, which, upon collision, vaporized into steam, adding to our planet's early atmosphere. The average mass of these comets was about 10 billion metric tons, each delivering not only water, but also complex organic molecules crucial for the emergence of life. Imagine standing on a moonless night under an open sky, gazing at the stars. Each one could be a witness to the chaotic era when Earth was bombarded by celestial debris. For billions of years, comets and asteroids rained down upon our planet, delivering not just water, but also organic compounds essential for life. Imagine these icy bodies hurtling through space, each carrying within them molecules that would eventually form the building blocks of proteins and DNA. A single comet might contain more water than all the lakes on Earth combined. Yet, it is this very water, delivered in violent collisions, that seeded our planet with the essential ingredients for life. Comets, often referred to as dirty snowballs, are composed primarily of ice and dust. When they approached young Earth 4 billion years ago, their impacts delivered vast amounts of water and organic compounds. Each comet impact released about 100,000 cubic kilometers of water, equivalent to filling Lake Superior 3 times over. These collisions occurred at a rate of 10 per day for millions of years during the early stages of our planet's formation. The debris. In the quiet dawn of 4004 BC, as stars aligned and minds awakened, we considered our place among cosmic patterns and celestial designs. And now, as this journey nears its end, let us gently drift back to that moment of wonder. Thank you for joining us tonight on Cosmic Sedation. We're grateful you were here with us. Feel free to subscribe and leave a like if you enjoyed the trip. Good night, Chinese letter, Chinese letter, Chinese letter, Chinese letter, Chinese letter, Chinese letter.